Okay, shall we get started? It's already time. We're going to cover interconnects today, as I promised, and this is a critical part of scalability in the system, as we've discussed actually in Subbus's guest lecture as well as distinguished colloquium. Let me go back over here. We'll discuss more about that next week. But I believe this will be the last full topic that we're going to cover in this class. Next week, we'll talk about next week at the end of the lecture. So please remind me to save 10 minutes at the end as to what we're going to do next week and some logistics, ... Okay, but I don't want to delay jumping into interconnects because there's a lot to cover here also. Actually, this is a course by itself as well. Clearly, there are interesting ways you can jump into other types of interconnects, like bigger interconnects in the world. And you will see a lot of resemblance to networks that we use in real, like large-scale systems today. But this is a summary of the last few lectures. We covered multiprocessors, memory ordering, cache coherence, and we had a guest lecture on robustness and next yesterday. Did you guys enjoy that? It was fun? Okay, now I'll keep pointing to people asking, answering questions then. But yeah, it's good to participate. Okay, today we're going to go into interconnection networks, and there's a lot to cover, as I said. But let me motivate it with using just one slide from the past. This is, if you recall, I think we covered this 2 weeks ago on cache coherence, right? And we had the two cache coherence mechanisms, broad. Snoopy versus directory-based. And if you remember, there are upsides and downsides to everything. And we may discuss the upsides and downsides to what Subbus discussed last time, yesterday, on next. Maybe we can do some of that next week. But with cache coherence, as you can see, Snoopy cache is good for missed latency. There's a global serialization point. The bus provides this already. We already started talking about interconnects, actually, right? When we were talking about cache coherence. Because you're connecting multiple processors, there needs to be some medium to connect them. And it's simple because you can adapt bus-based uniprocessors easily. The downside is it relies on broadcast messages to be seen by all caches. So there's a single point of serialization, which is bus, which is not scalable. That's essentially what this lecture is all about, actually. How do you actually design the interconnect to be more scalable at hopefully low cost and low energy? Okay. So directory, on the other hand, if you remember, you have a middleman that receives all of the messages for a given block, all of the requests for a block, and it basically arbitrates. It decides who gets the block, right? That's the way of thinking about the directory. So clearly, this adds indirection. As a result, it's slower. So your critical path for a single access is actually slower. And it requires extra storage space. And we went through the calculation, as if you remember, how large is the directory, right? And it turned out to be quite large if you want to scale up the system. If you remember that example at 200 megabytes or something like that per node. Okay, and then you can play tricks to actually reduce the size of the directory and run into other kinds of issues, as we've also briefly discussed. So there are a lot of trade-offs, as you can see over here. And clearly with directory, protocols and race conditions are more complex because things are actually more distributed, if you think about it. But the big advantage is it doesn't require broadcast to all caches, whereas this requires broadcast. And as a result of this, it's exactly as scalable as the interconnect and the directory storage. As long as you can scale the interconnect and you can scale the directory storage, this is actually a pretty good fit. So we've already clearly talked a lot about interconnect over here. Today we're going to talk about how to actually design that scalable interconnect. Does that sound good? Hopefully this is a review for everyone and you can think about the trade-offs. So these are some readings. There are a lot of readings here, and there's actually a lot of terminology in this area. I like writing papers without relying on too much terminology. That's why I'm going to give you this paper. Even then, there's terminology over there. And we're going to cover this hopefully toward the end over here. Okay, let's talk about some basics to begin with. First of all, why do we need an interconnect? Clearly, to connect components, as the word implies. It's interconnect. And interconnects happen at many, many levels. Actually, a wire is an interconnect, right? The thing that we talked about yesterday, the vias. They're interconnects. They're very short and very fast, but they're interconnects. And Interconnects connect processors and memories, processors and caches, within the banks and banks, I/O devices, everything, right? So there was this actually debate maybe 15 years ago or so in one of the computer architecture conference, HPCA, I believe. And the debate was about, what is the problem? Where is the bottleneck? Is it the processor? Is it the interconnect? Is it the memory? And people usually argued it's the interconnect or memory. I see these things to be very similar, actually. If you remember the memory latency lectures, we actually talked about interconnect quite a bit over there, right? We said the latency is due to this long bit lines. That's essentially an interconnect, connecting your memory cell to some other parts, the outside of the chip, almost, right? Or the row buffer. That's the bit line itself, and then you need a global bit line to take the data out. So those are both interconnects, except they're at different levels. One is the local interconnect, and the other is more global interconnect within the DRAM chip, right? So we actually have a lot of interconnect inside the memory. So where is the latency coming from? Well, it could be from the memory cell, it could be from the interconnect also. And to reduce some of that latency, we segmented the interconnect, if you remember, with the tiered latency DRAM idea. How many of you guys remember tiered latency DRAM? Okay, good. So tiered latency DRAM was you tier the latency, tier the segment, or segment the bit line. As a result, you isolate part of the interconnect from the other part of the interconnect. So if you think about it, this has nothing to do with the memory cell itself, right? It's really all about the interconnect. So this debate is very interesting from my perspective, because when you're optimizing memory, it's really about optimizing multiple things. And if you put computation over there, then you're back to everything in the end, right? You got to optimize everything if you're thinking globally. Okay, but we're going to focus on that wire itself today and how it can be designed to be more scalable. Okay, this is just one picture of it, as you can see, right? This is a multiprocessor picture. You have a network of computers, as you can see over here, right? But this could easily be on chip as well. Okay, why is it important? Well, there are multiple reasons. It affects everything, essentially. As I just said, it affects the latency. It affects the scalability of the system. This is the lead we have with the cache coherence to it. How large of a system can you build? If you have a bus, for example, you may not be able to build a very large system. And also, how easily can you add more processors, right? Again, if you have a bus, it may not be so easy for you to add the processors in there. It affects performance and energy efficiency. How fast can processors, caches, and memory communicate? So because it determines your latencies, it determines your bandwidth. It determines how much energy is spent on communication. And there's a really low-level perspective of this lecture that I'm not going to talk about, because there's a lot of low-level circuit level, actually even material and device level considerations in interconnects, right? What kind of interconnect do you build? Do you build copper interconnects? Do you build photonic interconnects? Do you build tungsten interconnects? ... We're not going to talk about that. That's why this is really a class by itself. We're going to assume we're going to be agnostic, actually, to the low-level organization of the interconnect, but that's clearly determines your energy, bandwidth, latency. So photonic interconnect. Well, if you want to make it energy efficient, we can defer this to later. Yeah, I don't want to go into the device itself. Yeah. Partially, it's because of the it's because of the conversion latencies, right? In the end, if you can do photonic computation, then maybe you can reduce the latency, but the conversion actually had a lot of overhead in terms of the latency. Make sense? Okay. Okay, so let me start with some terminology. If you actually go into interconnects, you'll see a lot of terminology, and it could be scary a little bit. But let's try to make this a bit easier. So there are some basics. These are the three major basics, in my opinion. You need to have a topology. You need to have a routing algorithm or mechanism, and you need to decide buffering and flow control, how you do those things. So what is topology? Basically, what does this thing look from the outside? Basically, it specifies the way switches are wired. How do you connect the different components? And we'll see examples of this. And this affects everything in the end. How do you route a packet from one place to another? How do you communicate? How reliable it is? Because how much path diversity you have, how much redundancy you have, for example. If one link fails, can you actually tolerate failure with some other link? What is your throughput? What is your latency? And how easily can you build it? And we'll see this with many, many different topologies. Bus is one topology, for example, right? And we've seen also meshes, two-dimensional meshes. That's another topology. But there are many, 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 many other topologies. So routing algorithm, basically how does a message get sent from a source to a destination? Right? And there are many, many choices here. One is, this could be static or adaptive, right? And we'll see examples of this. This is just one choice over here. And buffering and flow control answers the question, what do we store within the network? Do we store entire packets, parts of packets, etc.? And network is actually very general here. What do we store within the router itself, right? Or do we ever store anything in the router? And how do you actually communicate that something is congested so that people should not send stuff downstream? How do we throttle during oversubscription? So there are many questions over here, and we're going to cover some of these. But these three things are the key design choices that you have. And they're tightly coupled with each other, actually. There's some orthogonality, but for example, as we will see later on, if you don't want to have buffering inside your routers, your network topology needs to satisfy some requirements. And if this is cryptic, we'll get to that. Maybe you can think about it, right? What does that mean, right? If you don't have any buffers in the router, that means that you cannot store a packet that you receive, which means that you need to send it somewhere whenever you receive the packet, or you need to drop it. And those design choices affect what kind of topology you can actually have if you made your buffering choice that way. Okay, and clearly what I just described affects your routing algorithm also, right? Okay, let me give you more terminology. Networking, we're not going to use all of these, but it's good to set the stage. Network interface is the module that connects the endpoints. Endpoints are basically, we can consider things that inject into the network. In our case, we're going to look a lot into processors, right? But memory also can inject into the network, right? Response packets, response messages. And this decouples computation versus communication. And again, we're going to blur this a little bit also. Your computation is done, or memory access is done in one endpoint, and then communication is done on the network. Okay, link is a bundle of wires that carry a signal, a packet or message, for example, a switch or router. These are actually interchangeable. It connects fixed number of input channels to a fixed number of output channel. And a channel is essentially a single logical connection between routers and switches. I'm not going to formalize this more than it's needed. Let's keep things a little bit informal here, but you'll see examples of these as we go along in this lecture. Make sense for now? Okay. It's boring, right? Yeah, but it's good to set the terminology a little bit. So you'll hear the term node also. It's essentially a router switch within a network. It's different from an endpoint. Endpoint is essentially at the end of the network, whereas node could be within the network. A message is unit of transfer for network clients. So a processor sends a message to memory, and that message gets broken down into packets. This is a unit of transfer for network, and that packet gets broken down into FLIT. It's called a flow control digit. It's basically the unit of flow control within the network. How do you actually do the flow control? How do you prevent oversubscription? How do you ensure that the router doesn't receive more stuff than needed? So a FLIT can be the same as a packet. You don't need to break down a packet. Let's say a packet is 64 bytes. You don't need to break it down into 8-byte FLITs. You could say a FLIT is the same as a packet, right? Then you're actually increasing the granularity at which you're doing the flow control within the network. And we will see examples of this. Okay, there's some more terminology. Direct or indirect networks. Basically, in a direct network, the endpoints sit inside the network. Basically, things are inside, and you will see that. Everything is an endpoint, essentially. Whereas in an indirect network, endpoint sits outside the network. So this is one example of an indirect network. So you can think of these as, for example, processors, and you can think of these as memory banks. And these are not processors nor memory banks. They're just routers, switches. These enable you to connect any processor to any memory bank over here. Right? And you can see that this is not a terrible network. This is called a multistage logarithmic network. Essentially, you have 4 layers of routers. And if you want to get from here to here, you need to be routed somehow, right? You need to go through. There are multiple paths, I think, for that to happen. And you need to be routed. But for example, if you want to get from here to here, you should not get routed this way, right? There's no way to escape otherwise. And we'll see the reason for this, right? This is actually a more cost-effective network than a crossbar. But also it's more expensive and more scalable than a bus. So there's some more terminology over here. This is called a router. There you will hear the term radix. Radix is a radix of 2 means you have 2 inputs and 2 outputs, basically. And there's an abbreviation, radix array. So these routers are 2 array. N array means N is your radix. So you may actually see these in the network terminology. I don't like using this, but especially in our papers, we don't use it in general, but you will see it in the general terminology. Okay, so this is another example. This is actually a 2-dimensional mesh, if you look at it. And this is actually a direct network because every node is both an endpoint and a switch. Endpoint, remember, endpoint injects into the network. So you can see that every node can inject into the network. Here, the routers are passive. They basically route stuff, but they don't inject into the network. They basically pass through whatever they receive from these endpoints or previous routers. Make sense? Okay. So if I ask you what's a direct network and what's an indirect network, now you know. Okay, let's look at topology now without describing more terminology. Well, sorry. There's terminology within the topology also, and we will see some of these. I mean, we're not going to use this as much, but it could clearly be regular or irregular. And regular graph is a regular topology. But irregular, internet is very irregular, for example, right? There's no structure that's imposed on the internet network. Routing distance is the number of links or hops along a route, how long it takes to get from point A to point B. Diameter is the maximum routing distance within the network. So if you keep it short, then your latency is hopefully short. But that's not necessarily true, right? Because that depends on your wire latency also now. But it's usually good to try to have a short diameter network so that you don't have many hops, many switches to go through. And average distance is the average number of hops across all valid routes. Or, yeah, exactly, all valid routes. But, of course, you can also define average distance given a workload. If you actually have a workload that's injecting stuff into the network, it has an average distance, and that's dependent on the communication pattern that you have in the workload, right? Okay, clearly these are network-level metrics, so they're not necessarily taking into account all of the contention that we have, right? Distance basically doesn't take into account the contention you have. It just says, this is the number of links that I have along this source A to destination B, right? Okay. There's another metric that I will talk about, and I will not, I will say not so good things about it in the end, but a lot of people use this. This is bisection bandwidth. This is often used to describe network performance, and the basic idea is you cut the network in half and sum the bandwidth of links that you sever if you cut the network in half. Now, basically, you can formally define it as minimum number of channels spanning the 2 halves times the bandwidth of each channel. It's minimum because you need to find that minimum cut in the end. So this is meaningful only for recursive topology, and it's even meaningful if it's symmetric topologies, meaning wherever you cut it, your bandwidth is the same. That's more meaningful for those networks, right? But it can be misleading because it doesn't account for many things. So people used to describe networks as their bisection bandwidth. So this network has a much higher bisection bandwidth, so it must be good. That's not true, right? Because if you look over here, if you want to look at the bisection bandwidth of mesh, you cut it over here, and you look at the number of links and multiply the links by the bandwidth of each link. That's your bisection bandwidth. And you need to do it over here also. I think you go through here, for example, ... But it clearly doesn't take into account the congestion, routing, latency, ... So I'm not going to dwell too much on this one, but you should really know this name, bisection bandwidth. And certainly, it doesn't necessarily correlate with execution time, right? Actually, any of these that we discussed over here, they don't necessarily correlate with execution time because execution time is a much bigger component than just the diameter or the bisection bandwidth. It needs to take into account how fast your router is, how fast your link is, how efficient you are in your routing, how much congestion you have, ... Okay, there's one more term. I hope this is the last one, but I cannot promise. Blocking versus non-blocking. Again, we're not going to look at this as much. I'll just give you a demonstration later on. But if you connect any permutation of sources and destinations at the same time, If that is possible, then the network is non-blocking. Otherwise, the network is blocking. So basically, you can transmit between any source and destination at the same time, any permutation of those. That's non-blocking. And there's also something called rearrangeable non-blocking, which I'm not really going to talk about, but you can read the slides. This is boring. OK, let's look at some real topologies. Let's look at the more interesting things over here. But I will show you an example of non-blocking topology. For example, a crossbar is non-blocking, because crossbar, as at least a buffered crossbar, if you are buffering your crossbar, at any given point in time, any permutation of source and destination can be connected to each other. Of course, this comes at a cost, right? Whenever you start reducing the links in the network, you start making it blocking, as we will see. So a mesh is blocking, for example, because you cannot be doing that. OK, so these are some topologies. We're going to cover some of them. Actually, I think we're going to cover all of them here. But there are many, many others. Like the star is not here. There's a star topology, for example. That you can come up with any topology, right? This is actually very closely connected with graph theory. Any graph is a topology, essentially. Any arbitrary graph is a topology, actually. That may or may not be a good topology. But I can ask you, what's the topology of internet? I don't know, right? Somebody needs to discover all of those nodes. It's none of those, actually. Over here. But when you build a supercomputer or when you build a multi-core chip, you need to have a topology, right? So this lecture is actually has many stories, right? I could tell you this lecture from a very supercomputer perspective, because this is extremely critical when you build a supercomputer. Because if you think about connecting, I don't know, 100,000 nodes, then this becomes a critical component, right? And actually, a lot of interconnection networks and its terminology has been developed in terms of supercomputers, because that's where interconnect was really, really important to begin with, even before the internet, right? For example, Cray 1, right? That was a supercomputer, and people added multiple nodes. OK. Actually, this hypercube, we will see, it's the first, it was developed for the first message passing computer that we know of, at least. OK, so let's talk about metrics a little bit also, because whenever you're designing a topology, you cannot avoid metrics. We need to talk about three things in particular a lot. Cost of the topology, that was really important in the design of a supercomputer. So people may tell you the government sponsored the supercomputer and they didn't care about the cost. That's wrong. They always care about the cost. If somebody tells you if somebody doesn't care about the cost, you should always question that. In the end, cost is really important, even if you're designing a billion Swiss franc supercomputer, because cost can actually increase very quickly. And as we discussed yesterday, energy is also a cost, right? That's not over here, but I added it over here. But I'm not going to analyze the networks based on this, because this is much more complicated than just link cost or router cost. OK, latency, at least average latency, this could be measured in hops or nanoseconds or whatever. It could be minutes also if you have a huge network. And contention. And there are many other metrics that exist that you should think about: energy, overall system performance, bandwidth, ... And then energy delay products, combinational metrics, as we also discussed yesterday, right? Some of these. And people have also developed other metrics like energy delay square, ... But we're not going to talk about those either. OK, let's start with the first topology that you've seen, the Subbus. It looks nice and boring, right? And this connects 8 different processors or nodes, as you can see. In this case, there are endpoints, so they can all inject into the bus. But only one thing can inject at a time. So they need to arbitrate. Clearly, I'm not showing the arbitration logic over here for the bus, but it needs to exist because it's a single medium. Oh, what's happening? So all nodes are connected to a single link. In this case, it's another example of a bus, right? This is commonly used in multiprocessors that look like this. As you can see, this looks like caches are connected and they're snooping onto the bus, right? This is beautiful for cache coherence, Snoopy cache coherence. So what are the advantages? It's clearly simple, right? Conceptually, it's simple also. It's beautiful. It's cost-effective for a small number of nodes. Clearly, you don't have many links. And you can pipeline the bus also. That adds a little bit more complication, of course, right? And it's easy to implement coherence because you can do snooping and serialization on the bus, as we've discussed before. So hopefully this is clear. Now, we also discussed that this is not scalable, right, to a large number of nodes for multiple reasons. You have limited bandwidth, right? And actually, bandwidth becomes even more limited as you add nodes. Why? Because as you add nodes, you're loading the bus electrically more. And you need to reduce the frequency if you want to operate it correctly. So this is exactly not what you want if you want to scale the network. Your frequency needs to reduce as you keep adding more nodes. And also, if you think about a non-pipelined, non-partitioned bus, simple bus like this, your throughput is actually pretty bad because you may be communicating between these node 0 and node 1 only, but you're occupying the bus, right? Somebody else cannot communicate over here, right? Now you can solve that problem by doing partitioning, but that complicates the design now. It's not a simple bus anymore. Okay? And if you have high contention, as a result of what I said, you get fast saturation. The network gets saturated, that's another term, very quickly, because if many things are communicating at the same time, then you have a single medium. They all have to be serialized, right? And I think I'll go back to the thing that I said earlier. One of the biggest problems is you don't have independent communication is not allowed, right, on this medium. 0, 1 cannot communicate with each other while 6 and 7 are communicating because you have a single medium. And all of the other networks try to solve this problem in the end. Okay, so let's look at the exact opposite extreme, right? And the other extreme is point-to-point connections, right? Every node is connected to every other with direct or isolated links. There's no sharing of the link. You have isolated links. So 0 is connected separately to all of the other 7 nodes. Similarly, 1, similarly 2, ... That's beautiful also, as you can see. Now, clearly this has lowest contention, potentially lowest latency. It's ideal in terms of some metric, performance perhaps, right, if cost is not an issue. Right? Now, cost is a big issue, of course. You have very high cost over here, right? You have ON connections from each node. Connection can also be called a port, but we will see more ports later. And ON square links, as you can see. And also there are other, I'm not being comprehensive in all of the downsides over here, right? You could actually add, or even the upsides over here, but one of the other downsides, how do you actually do Snoopy cache coherence over here? I don't know. If these are the only connections you have, can you actually do Snoopy cache coherence? That's a good question to think about. Maybe this is not the network you want for Snoopy cache coherence, right? Does anybody have a solution? It's not an easy question. Okay. And it's also not scalable because of the cost reason, essentially. Bus is not scalable for a very different reason, because your performance actually reduces as you keep adding nodes. Here, your performance increases, but your cost increases even more, as you can see. Right? Okay, and there's another question. If you actually do this, how do you lay out on a chip? I don't know. Maybe you have a solution to this. Because it's not, as you can see, it looks regular, but the layout is going to be a mess over here. And if you have 1,000 by 1,000, well, 1,000 nodes, then it's going to be even worse. And actually, this is a problem even in supercomputers also. Let me switch to supercomputing a little bit. Even if you're not on chip, you have these big wires that you need to connect across, I don't know, 10,000 nodes. Let's say you're building a 10,000 node supercomputer. Now your wiring becomes complicated. Actually, some people calculated, and they showed that the cost of the network is usually in that wiring that you do. And a lot of reliability issues arise because people who are doing the actual wiring of the nodes miswire. So a big problem in those big supercomputers is actually how do you actually ensure that the wires are wiring is correctly done across different nodes. And if you have something like this, you have a lot of wires. And you need to connect the right thing to the right thing. I mean, it's possible you color the wires, of course, right? But that's a lot of wires to deal with. Okay. Do I want to say anything else over here? Any other thoughts? Okay. Clearly, I've given you the two extremes on the end. Now we're going to try to look at the middle. Okay. So this is middle coming from this side, not coming from the bus side. So how can we make this a little bit more cost-effective while keeping the lack of contention, right? And the next step is really crossbar. In the crossbar, every node is connected to every other with a shared link for each destination. So for each destination, let's say destination 0, you have a shared link. And to that link, the individual, basically individual other nodes can tap into and send requests to. For example, in this case, if node 7 wants to communicate with node 0, it sends a request to the shared link. And if node 0 over here, let's say processor 0, memory bank 0, I like thinking about it that way. If they want to communicate, then 0 sends a request over here. And both requests can exist on that shared link, right? Because you may have buffering in that link. Make sense? So in this case, it's clearly not point-to-point. You have a shared link per node, and it's two-dimensional because the other ones, the inputs also need to connect to that shared link. As a result, your cost has reduced. But now you can have, here you had completely concurrent transfers to different destinations or the same destinations. Here you can also have concurrent transfers to non-conflicting destinations, right? Even for the conflicting destinations, you can have concurrent transfers, but at the end, you have to have some serialization, right? Because both of them are sharing some input, some port over here. As a result, if 7 is connecting to, 7 is sending a message to 0, and 0 is also sending a message to 0, at some point, they conflict with each other, right? But that's at the very end over here. You can design the big part of the substrate such that there is no conflict. Make sense? Hopefully that's clear. And this could be cost-effective for a small number of nodes again. I mean, this could be cost-effective for a small number of nodes also, right? Okay, so what is the upside? You get low latency and high throughput actually compared to a bus. If you think about it, this is actually a two-dimensional components of two. You have two, again, ON square buses over here. But it's expensive again. It's not scalable because the ON square cost that you have over here. Does that make sense? You have n-square routers essentially inside the network. And one of the downsides is over here, if you look here, it's relatively easy to arbitrate actually because you have point-to-point links. But now you have an arbitration problem on the shared link, right? You need to somehow have a mechanism to share this link that you have. And people have developed a lot of mechanisms. We're going to look at multiple of these very quickly. Okay, as n increases, actually, the arbitration complexity also increases. You really want to have this distributed arbitration. And if you have distributed arbitration, at some point, you'll need to deal with the contention that happens at the input to this node. Right. Okay, this is actually used in real systems. I mean, clearly, bus is also used in real systems. Point-to-point could be used in real small-scale systems. But this is used in real multi-core processors to connect cores to caches, and I'll give you examples of that. Because this leads to the lowest contention, and if you actually have a lot of traffic between your core and the caches, you don't want to put that bus necessarily over there. So this is another crossbar design, if you look at this. These are, the red parts are the shared links to the destinations. And again, think of this as processors, cache banks, right? Now it's more clear. It could be memory banks, it could be anything. It could be processors and other processors, right? But in this case, these are example arbiters. Somebody needs to decide the inputs of these arbiters. These are enable signals, right? You're enabling the gating of this signal onto this bus. So if 3 is transferring to 0, you need to enable this, and somebody needs to ensure that the other links are not enabled. Now, this is an example where you don't have buffers over here, where only one source can transmit to a shared destination. But now arbitration complexity, you can see there. I'm not showing the arbiter over here, but everybody needs to communicate with an arbiter here. And that arbiter actually needs to grant the signal. And that could have its own pipeline, or that could be done in a single cycle. There are a lot of design choices, as you can see over here. But even with this design, now we are enabling concurrent requests to different destinations, right? You can have 8 concurrent requests over here. But whether or not you get 8 concurrent requests depends on your communication pattern clearly, right? Everybody, all of these 8 nodes over here may be requesting one single destination, a single bank. You have a bank conflict, then you're serializing all of them if you have the design bufferless like this. So here you're not buffering the requests that are coming from the nodes. Okay, So this is a different design. It's not exactly the same. It actually has buffers. But I'll show you the example here. This is one of the earlier multi-cores, Sun UltraSpark T2. That's Niagara 2. Niagara 1 was the really wimpy multi-core design, if you remember, right? The cores were really simple. And Niagara 2, they made the core, and all of the cores shared a single floating point unit. In Niagara 2, they figured out this was too low performance because a single core performance is not good. So they added a shared, they actually replicated the floating point units, for example, and they actually added branch mechanisms, But we're not going to talk about that. We're looking at the core to cache bank network. These are the 8 cores. These are the 8 different banks in L2. And how do they communicate with each other? Well, essentially, this is a network that you see over here. Actually, it's 8 cores and 9 banks. I shouldn't say 9 banks. It's 8 banks plus the non-cacheable unit, because there's a direct connection to memory as well. So essentially, this is a crossbar. And you can read the Niagara 2 paper, which unfortunately I don't have a reference for, but we will put a reference to, as to how this exactly works. But they essentially have a 4-stage pipeline to do this communication. Basically, they have a crossbar, but to be able to get onto the crossbar, you need to first request it in the first stage, and then you arbitrate for the crossbar, and the pipeline selects one of those that needs to go on that shared link, and then you transmit in the next cycle. So it actually takes 4 cycles to do that. And you have a 2-deep queue, so you have some buffering. This thing I showed you here, these are gate-enabled signals. This doesn't have buffering. But you could imagine having buffers over here, right? Whenever 0 wants to request the destination 0, you have two buffers over here. You can have 2 requests outstanding. 0 can have 2 other requests outstanding here, 2 other requests outstanding here. So you can have actually 2 buffers in each of these, such that you don't need to wait stalling over here. You can keep injecting requests as much as you have buffering, clearly. So Sun UltraSpark T2 had 2 deep buffers for each source destination pair to hold the data transfer request. So the core didn't need to stall for the lack of availability of an interconnect link. It could keep buffering. So clearly, you could add more buffers. Now your network cost starts increasing. So what I've shown you essentially is 2 different designs for the switch. This is one design for the switch, bufferless. You have these gate-enabled signals, and you enable or disable based on some arbiter logic that's magic somewhere here. Or you can have buffers in each of these points, cross points, let's call them. And somebody needs to still do the arbitration, and the arbitration comes after the buffering. Basically, arbiter needs to look at the head of those buffers and decide which one should take the link. Okay, so you can read this paper if you want to learn more about this. Actually, I've already given you this example, but this is a nicer example maybe. Okay, this is the buffer. What's the difference between a bufferless and buffered crossbar? Bufferless is you need to have the arbiter ensuring that only one request occupies this link at a given time. So for example, if this network interface is trying to inject into this red link, this network interface is also trying to inject into this red link. They need to be serialized, and there needs to be arbitration that happens. But this green one can go because there's only one green one that needs to be injected. In fact, I actually forgot this one over here. As you can see, there are 3 of these that need to be injected into the red link, and they get serialized over the course of 3 cycles. Whereas this one can go in parallel, concurrently, in the first cycle with one of the red ones. So clearly, your throughput is lower if you don't have buffering, right? That's very fundamental. Because you cannot keep injecting. Clearly, you're blocked at the injection time. Eventually, with buffering, you need to be serialized perhaps over here, but you need to be serialized maybe somewhere else at the bottom. Again, that's a design choice. Okay, let's look at the buffered version. Essentially, the buffered version looks complicated, clearly. You have buffers in each of these cross points, and you can inject into the buffers. That's nice. And you could actually have something like this. The core could be running ahead, if you will. It could really be running ahead, or it could be doing something else. It could be switching to something else, But basically, as you add these buffers more, your potential throughput increases, both in the network as well as the system. But now you still need to have arbitration complexity. You need to arbitrate as to who gets the link in terms of these buffers. And you have another level of complexity, which is flow control, right? You need to communicate the lack of buffers over here. So we didn't get rid of the complexity of that arbiter. We just pushed it somewhere else, saying, oh, I don't have an available buffer, so don't send it to me. And we'll see a lot of flow control techniques later on. There is not a single way of doing this. Okay, the upside is a bit simpler, actually, because now you can actually do the arbitration inside the network as opposed to over here. And also, you could partition some of these things much more easily, whereas if you have a real single medium that looks like this, partitioning is a little bit harder. Because you don't have any buffers, if you remember, right? You don't want to add switches. If you don't have any buffers, or if you don't want to add switches, then you really need to arbitrate across all of these things that are trying to inject onto that single link. Whereas here, now you have buffers, you can actually do partitioning, right? So you could imagine, oh, this, I have some partition over here, I have a pipeline register, ... But this becomes more complicated, clearly. But the design is very, the design choices are very large, as you can see, right? As architects, we have many, many choices here. Okay, so, okay. There's another advantage of this sort of buffering. Now you can have variable size packets nicely, right? Before you could inject, or it's somebody else's responsibility to break things down such that you have, you can inject only packets that are the same width as your wire. This could be 64 bytes, for example. But now you can inject whatever your flit size is. Your flit size may be, I don't know, 8 bytes over here, and you can inject 8 of these packets, 8 of these flits. Remember, flit is the flow control unit. Flow control is done at the granularity of that thing. Okay. And I haven't talked about the output arbiters, but I've talked about it before, right? Somebody needs to arbitrate for the destination link over here. Okay, the downside, as you can see here, now you require n-square buffers. So if you want to increase throughput, there's no magic. You need to pay the cost. Okay? And this may come at the expense of latency also, because now you have these levels of buffering, ... Okay, so even this simple crossbar has many, many design choices, as you can see. But we're not going to cover more of these design choices, but we're going to ask some other questions. And one question is over here, right? Clearly, this is high cost. Can we still, actually, people devise these crossbars, again, for supercomputers, and they said this is too costly. So can we get something simpler? And the key question is, can we get simpler yet still have low contention compared to a bus? Because a bus is not scalable, it has a lot of contention. The idea of multi-stage networks got developed because of that, basically, when people ask this question. And a multi-stage network looks like this, basically. It's an indirect network with multiple layers of switches. Crossbar is an indirect network also, because these points are not endpoints, right, over here. Clearly, these are switches that are passive. They don't inject into the network. Multi-stage network, it has multiple layers of switches between terminals and nodes. And these layers enable more scalability because you don't actually have this crossbar type connections over here. So you have switches in between. So if you look at this is an example network, Omega network, and we're going to see some of the other ones. But basically you have the first layer. It takes 2 inputs and 2 outputs. So the radix is 2, as you can see, of each layer. And it has a particular connection that enables every node to be able to communicate with every other destination node. But maybe you cannot do it all concurrently. Right? So it's blocking in this case, as you can see, right? The previous crossbar, all of them can do it concurrently, assuming you have enough buffering. Whereas here, you cannot do it concurrently, as we will see. But this is, again, people have actually looked at optimizing this based on multiple ways, both theoretically and both practically. But let's take a look at an example. If this memory, if this processor wants to communicate with this memory bank, let's say, actually these are heavily used in processor memory bank connections in multiprocessors in the past, and they were developed especially for that purpose. How do we connect these processors to these memories such that we get the lowest contention, but we're scalable as well? So this processor wants to communicate this with this memory bank. There's one path. Actually, this is the only path, I think. There's no other way you can get to that bank. So clearly now our path diversity is limited. And if you look over here, that processor wants to communicate with that bank, and they conflict with each other inside the network, not necessarily at the endpoint, right? Actually, at the endpoints, there is no conflict, as you can see. Assuming if they didn't conflict here, they could have gone completely independently, but because we reduced the cost of the network, they conflicted at this output port. If the requests both arrived at this router at the same time, they get serialized. This should not happen in a buffered crossbar, right? Unless your buffers are full, of course. Make sense? Okay. So you need to handle those conflicts. So the question is, I already told you the answer, right? Is this blocking or non-blocking? Clearly, this is blocking. Blocking means any permutation of source-destination pairs can concurrently transmit at the same time. And clearly, that doesn't happen when you have conflicts. And as your injection rate into the network increases, depending on your patterns of access, your conflict rate also increases. And the art and science is really figuring out how to make this give you high throughput while minimizing the cost of the network. Okay, so this is another example. Actually, we're going to talk about circuit switched versus packet switched in a little bit. But this is actually a butterfly type of network. We're going to look at that also. But you can see that it consists of 2x2 crossbars. It's actually pretty simple. The crossbar you have, this is the network itself contains, the switch itself has a crossbar in it, right? The inputs are 2, the outputs are 2, and any input can be connected to any output at any given time. And this multi-stage network has more restrictions on feasible transaction receiver pairs compared to a crossbar, and that was obvious in the previous example. But it's also more scalable than crossbar in terms of cost. So for butterfly, it's O n log n. Actually, a lot of these are n log n. So this one is also O n log n. And latency is log n. N is the number of nodes. Clearly, the latency is proportional to the level of network, the number of switches you have between the source and destination. And the number of switches is proportional to the logarithm of the number of nodes. Does that make sense? So clearly, if you had 4x4 crossbars, this would be still log n, but log to the 4n in that case. Right? Okay. I think I want to say everything over here. So there's another choice, circuit switching versus packet switching. I want to cover that over here. I mean, clearly, this is a big choice that people had for the internet, and they still have it, actually. Do you do circuit switching versus packet switching? Basically, circuit switching says, actually, circuit switching goes well without buffers. If you're transmitting from 0 to 7, for example, first you send a message that sets up a path. And that path is exclusively used for transmitting from 0 to 7. Whenever 0 injects a request going to the 7, it uses that already set up path. So setting up the path, how does that accomplish? That depends on, of course, your infrastructure over here, but it basically switches, it connects these routers in such a way that this input is always connected to this output, and this input is always connected to this output, this input is always connected to this output. There's no arbitration that's done. You set up the path, and then let this communication from 0 to 7 happen until the 0 decides, oh, I want to tear down the path. Does that make sense? Basically, this is called setting up a circuit. You set up the circuit, and it's smooth. Whenever you inject something, there's no arbitration overhead, because you know that this port, when it receives something, it directly transmits it over here. Okay? So this is good for, if, for example, 0 is sending a huge message. Let's say the message is 1 megabyte. If you're copying a 1 megabyte of data from here to here, and your link width is 64 bytes, it takes a long number of cycles. And if you set up the circuit, basically it takes 1 megabyte divided by 64 byte plus your connection setup and tear down overhead to do this. Right? But that's the beauty. You don't, for every single packet that you send, and if you do the calculation, that's 2 to the 20 divided by 2 to the 6, right? You're sending really 2 to the 14 packets. And for those 2 to the 14, you're not doing any dynamic switching overheads. The router is not deciding for every 2 to the 14, oh, should this go here or should this go here? No, it's already done, decided. You already set up the path. For all of those 2 to the 14, there's no other decision to make. So it's much more energy efficient if you're doing this sort of communication, right? Packet switching, on the other hand, you don't set up the circuit, yet packets hop from router to router pending availability of the next required switch and buffer. So it's more flexible if you think about it. If you did this, we wired the circuit such that it's only doing that transfer between 0 and 7. So if somebody else wants to transmit to 6 through this path, well, too bad. They cannot, because this connection is hard. I don't want to say hardwired, because it's really switched to 7, but it's switched until it's torn down. Right? So it's fast because it gets rid of this arbitration latency for all those packets, but now it causes conflicts because nobody else can transfer through this circuit that was set up. Okay? Whereas okay, let me go back. Packet switching is much more flexible. You don't set up a circuit. Every router makes a decision, where should this packet go? If you're transferring 1 megabyte of data from here to here, for every single packet, you need to make that decision. But the beauty of it is, while you're making that decision, some other packet may come over here, and then this router can decide, oh, I'm going to prioritize this packet such that this goes down that way. Right? So you could actually make very fine-grained decisions as to whom to prioritize that in that case. Make sense? Okay, but your router is also simple right now, right? More complex right now. With circuit switching, you can actually reduce the complexity of a router because it needs to be able to do circuit switching. That's it, set up the path. But then no dynamic decision. Right? There is no dynamic decision other than the circuit switching decision. How do you set up the circuit? Okay, basically, let's look at the upsides and downsides. Again, this is very general, right? Actually, Internet employs both circuit switching and packet switching. This is the dominant part. But you could actually set up your own network that does circuit switching. Right? There's no reason not to. Actually, if you're doing the communication that I just mentioned, huge amount of data streaming to some other node, you're much better off doing circuit switching, right? If you're streaming a lot of video and you have control over the network, you'd better do this right, for energy efficiency. And I'm sure some of those big video servers are doing things like this, actually. They're not doing packet switching internally. But once you get off the internet, it could be anybody's control. As a result, you may be doing packet switching. Okay, once you get off your own network. Okay, basically you set up full path before transmission, you establish your route and then send data. No one else can use those links while the circuit is set, as I said. Whereas you route each packet individually, possibly via different paths in packet switching. So that's another advantage, actually. You possibly go through different paths. You don't have to go through the same path. With circuit switching, you set up the path, you always go through that path. If the link is free, any packet can use it, so fine-grained link utilization is higher. So the upside of this, as I said, is faster arbitration. Your routers are faster now. No buffering, so you could actually get rid of all the buffers. It's beautiful. The downside is setting up and bringing down the path takes time. Right? So do you want to do it if you're sending only one packet at a time between one node and a destination node, that setup overhead becomes huge now, because you first need to send a packet to do the setup. There's a special control packet that you need to send to be able to do that, and that takes time. And if you set up the path just for a single 64-byte packet, let's say, well, it's a waste of time. That's a handshake overhead. The downside over here is it's potentially slower because the switch must dynamically switch the router. It needs to always make this dynamic decision, where should I go? So arbitration complexity is higher here. And you need, well, that's not true actually, but for now, let's assume that you need buffering, but that's actually a design choice as well. But here, definitely you can get rid of buffers. But buffering actually helps packet switch networks a lot. The big upside is there's no setup or bring down time. So in a sense, this is more general purpose because you don't want the setup and bring down time for very small packets. It may be good, it's okay, maybe it may be okay to pay this cost once and amortize the cost over a huge video, for example. I don't know, a 1 terabyte video. That may be okay, right? Whereas if you're sending only 8 bytes, this is much better, right? And this is more flexible. It doesn't underutilize the links. because of, well, I guess I don't have the downside over here, but this is really a downside. No one else can use those links while the circuit is set. Well, it's an upside and the downside because it enables isolation for this flow, and as a result, it enables the fact that you can do faster arbitration, but it also disables this fine-grained link utilization that you could otherwise have if you made the decision dynamically based on all of the packets that you received. Make sense? Have you guys covered this before in networking? Or who's taken a networking course? Okay, not many people. Who knows about these things? Okay, that's good. We're covering it. So if you take networking, you'll actually cover the higher level decisions of this, and there are other trade-offs here. I mean, not necessarily, right? No, not necessarily. They could be shared. I mean, we didn't even touch the core part, right? There are other decisions that you need to make. We are assuming that somebody is injecting stuff into the network. But what you're saying is actually very valid because now what's happening in the core may matter as well, right? Because there may be different threads that are injecting. We didn't even touch those things at the moment. But what you're saying maybe is actually interesting because maybe a lot of these things need to be aware of the application or the hardware context that's generating these requests. And that's absolutely true. I agree with that. You may actually make a decision over here and form the circuit, and then the operating system takes out the thread that formed the circuit. And what do you do, right? So there needs to be some coordination if you're designing a full system. So that's absolutely true. Right now, we're looking at it from a network-centric point of view, which may not be the best perspective if you were optimizing the overall system. These are good things to think about. We're going to get back to that later on in some other way. But in the end, I think if you really want to design a full energy-efficient system, you really need to optimize the network and the core together. They need to be aware of the decisions, because you don't want the operating system descheduling a thread that's doing huge communication that has set up the network. Okay, so this, I've taken an aside. That's why this styled an aside, actually, because circuit and packet switching has nothing to do with the topology, right? and we're talking about topology. I just took advantage of this multi-stage networks to talk about circuit and packet switching. It's really a choice that's independent of the topology. It's a higher level protocol on how a message gets sent to a destination. However, some topologies are more amenable to circuit versus packet switching, and I'll let you think about that as we go over the topologies. There's a bus, for example, a circuit switch network. I don't know. That's interesting because bus is so simple, right? We normally don't think about it. But there's an arbiter over there. I guess at a very fine grain, it's circuit switched. But you could actually make it even more circuit switched, right? You could say, I'm going to reserve the bus for the next 1 million bytes. That may not be a good idea, but it's possible. It could turn it into a circuit switch network. So essentially, it's really a higher level decision that you make. You have a question? Yeah. Go ahead. Yeah, certainly. I mean, I didn't. That's why I said I'm not going to go to the low level of these things. But certainly at the low level, there are many, many design choices. How do you design the links? Do you operate them always at the same frequency? Do you change the frequencies? People actually talked about that. How do you make them really energy efficient? There are actually a lot of work that goes on at the very low level, device and circuit level. Low swing interconnects, for example. You minimize the voltages. But that's a complete course by itself. We could have a complete course on this. We could have a complete course on reliable system design. That's something I always wanted to do, actually, add a dependable systems course, but maybe we'll do it at ETH at some point. We'll see. Yeah, there's a lot of research at the low level, sure. And I can point you to it. Say it again? Yeah, I mean, people actually optimize these interconnects very heavily, even in existing chips, so that they're very low power. Even then, they consume a lot of power. I can point you to papers. Okay. Okay, I already discussed. So let's go over some of these other networks. So this is actually one of the older networks. This I like a lot. This is the Delta network. You can read the paper. I like it because the paper is very nice. You may have heard of this name, Janak Patel. Do you guys remember? Let's see your recall ability. Where do you remember him from? No, that's not him. There's an aliasing that happened here. Take another guess. No, she's saying the same thing, but that's not true. Yeah, you read some paper from him. That's correct. No, you guys are... This is another Patel. He's not that old. This is an old Patel. But you did read his paper also, that's true. But this is the MESI protocol person. Remember the Illinois protocol by Papamarcos and Patel, ISCA 1984? So this is Janak's work on interconnects, even before that, actually. This is one of the really, really early works on multiprocessor interconnects. You're thinking about Sanjay Patel, who did the trace cache design. Oh, they're aliasing. Yeah, it happens. Okay, anyway, but if you look at this is another sort of network, Delta network, which is different from the Omega network. It has different properties, which we're not going to go into. I mean, you could actually make this really theoretical and figure out all these graph theory kind of properties of this, which may or may not be useful. In my opinion, they're not a lot useful over here in this context because you're very much workload dependent on whether or not those properties get exploited or not exploited. Essentially, this is, again, a radix of two networks. And this is one of the first networks that was proposed to replace costly crossbars as processor-to-memory interconnect. And the only reason I'm showing it to you is to show the variety of connections. These are different connections, actually. You can yourself come up with your own connection. This is Omega network, which we just set, which I just showed you earlier. Basically, in this case, single path from source to destination. All stages are the same, as you can see. Actually, in this case, all stages are not the same. I think that's one difference that you have over here. The connections are different. For example, here you go that way, and here you go this way. So they're not exactly the same. Here, I think they're all the same, but I may be wrong. Okay, it's used in the NYU Alter computer, and I'm going to bring that in a little bit to give you something a little bit aside. Basically, one of the things that they did in this computer was actually do operations inside the network. And the idea was to, if you're operating on a shared memory location, and if you see multiple operations going on to that shared memory location, you combine those operations. This is called combining operations in general. It was first employed over here. And one example over here is test and set, right? One synchronization primitive. And you can turn that into fetch and OR. So if every processor in the system is trying to get a lock, for example, test and set, you could turn that into fetch and OR operation that's happening in the network. Because all of them are actually trying to access, assume no caches right now, trying to access the same memory bank, and there's a lock over there, and you're basically trying to test whether that lock is true. If it's not true, you set it to true. That's the test and set operation. And if you set it to true, then you get the thing, and you get you can turn that into a fetch and OR operation, which essentially operates this way, right? Well, I don't know what this is, but basically you store the data over here, and if two things are trying to do the same operation, you basically combine the operations and give the correct result to each of them inside the network, as opposed to each of them fetching individually in a serial manner, one after the other. Right? So this works actually, this is actually generalized to fetch and add operations. I'll give you the more general form. Fetch and add M, I. You return M, and you replace M with M plus I. Right? So why could this be useful? For example, if you're having parallel processing, and if you're trying to modify a shared variable, it works with test and set, fetch and OR. That's easy, actually. But let's say whenever you're starting a program, one of the things of the task manager, if you have a dynamic tasking program, is to divide the array to different processors, right? This processor starts from array location 0. This processor, let's assume that you have 16 processors, and you're dividing a 1 million entry array among those 16, and you need to distribute the indices to the different processors. You don't set them up statically, but you dynamically distribute them. So the first processor, what each processor needs to do is get the latest copy of the index incremented by the amount that it's eating up from that index, which could be equal or not equal, depending on the load of the processor, let's say, depending on how it's programmed, and then write back the index, such that the next processor can start from the right position in the array. Does that make sense? That's essentially distributing the task. And this turns out to be a serial bottleneck, actually. You may parallelize everything else, but this is a serial bottleneck. You're operating serially on this dynamic tasking where you're dependent on that index update. Now, what usually happens in these parallel processors, and what these folks from NYU Ultra Computer actually figured out was, this turns out to be a huge contention in the network. Each processor gets this index, updates it, and then writes it back, and then the next processor requests it. So there's a lot of contention going on in the network, requests going on for this particular index value. So if you add something like this in each router, and when the router sees fetch and add requests from different processors, it basically performs this operation. It stores the value M over here. When it sees a request from a processor, it returns M, and it replaces M with M plus I. And if another processor actually gets it while this is in this router, it gets M plus I now. Make sense? So you should read the paper for more detail, but this is actually a beautiful operation. It's used in some other networks also, supercomputer networks especially, but this was the first instance of it. And this also shows you the importance these parallel computing folks have actually placed onto the serial parts of a program, right? Again, we talk about Amdahl's law all the time, and you've hopefully read Amdahl's paper. This is exactly the reason Amdahl's law is important, because it actually leads to things like this. But the other interesting the other reason I'm telling you about this is an example of where people do operations in the network. So far we've treated switches as dumb things, if you will, but this is not necessarily dumb. Maybe it's not extremely intelligent, sure, but it's doing some operation, right? So now you can imagine maybe other operations done in these switches, right? Because the data is, these switches are actually carrying a lot of data. Does it make sense for them to be dumb, right? It's very similar to the concepts that we've covered in processing in memory. Okay, we already discussed this. And the paper has analysis actually as to how much they reduce the synchronization latency. I didn't assign this paper because it is not so easy to read, in my opinion, but you can take a look at that. Okay, let's cover some more of these networks. Butterfly. Have you guys looked at butterflies? I mean, not real butterflies, but butterfly networks. Yeah, basically they look like this. So as you can see, they're very regular, right? Here you have these big connections across here. Now localized connections, more localized connections, and more localized connections. So it's actually, if you've done fast Fourier transform, it looks like this, right? So it's a good fit for fast Fourier transform. Computations can be mapped to these different networks also in an easy way. So if you can see, this is indirect, used in BBN Butterfly. BBN was a big company. It still exists, I think. I don't know what they do. Actually, I had looked at them, but I forgot. Maybe they're not doing anything interesting to me at the moment. So, I mean, one of these things, I'm giving out another term over here. You may hear the term tree saturation. It has nothing to do with trees, in my opinion. But basically, you get conflicts in this network. As a result, you get saturation. Now, that saturation actually affects many networks. So if you look at this, it's really like a tree. That's why it's called a tree, but it's really not a tree also, right? Because the connections actually get sparser, get more localized as you go down the network, which is very different from this one, right? There's no localization as you can see over here, right? For example, this goes here, which is really not that localized, except the switches are all the same here. Okay, we're not going to cover all of these things. But basically, you may get tree saturation if you have a lot of congestion on this part, for example, because this is the head of the tree, if you will. And if you actually do randomization in the route selection somehow, and you have a lot of potential routes here, that reduces that saturation. So how do you reduce the conflicts is a bigger question over here. And how do you select your routes? So do you actually go from here to one node, or do you go from somewhere else? I don't know. Okay, we're going to look at that later. That goes into routing, actually. So this is where your topology gets close to routing. But let's cover some of these topologies very quickly. So we've seen crossbars, we've seen multi-stage logarithmic networks, and we've seen meshes. Well, the names are obvious, hopefully. And this particular one is a butterfly network. Whether it's a direct or indirect network, I'm not going to quiz you on this at the moment, but I already said this. This is a direct network. These are indirect networks, as you can see. And these are, this is non-blocking, because all permutations can be present at the same time. They can transmit at the same time, with some assumptions, of course, right? If they're bufferless, maybe they're not non-blocking. But these are blocking. Clearly, there are many, many conflicts over here. Well, why is this a direct network? Because every router is also an endpoint here, as we've discussed. And this is the cost. Remember, we were trying to reduce the cost compared to here, get close to the bus. And we did get close to the bus with this one, right? And actually with this one, we're even closer to the bus. And latencies are unfortunately growing, though. And I'm not going to go through the calculations. You can look at clearly this is log n, right? And this is also square root of n. But your average latency is dependent on the workload in the end, right? But it's still an order of log n over here. It may or may not be an order of square root of n here. Actually, if you're doing neighbor-to-neighbor communication, your latency is really O1 right here. So, whereas here, your latency is kind of independent of your communication pattern, right? Okay, that's not always true. That really depends on what kind of path you provide over here. But there is also the question, right, applicability, right? Here, for example, it's much more general purpose if you think about it, because everything can be an endpoint over here. Whereas here, not everything is an endpoint, right? This is, if you think about it, this is a little bit more of a better fit for core-to-cache, core-to-memory networks. Core-to-core networks, maybe different sets of cores, makes sense. But if you're communicating between these two cores, maybe you should have some other network, right, locally. It doesn't fully apply over here. So these two were really developed for core-to-cache networks, or a set of cores to another set of cores type of networks. Whereas here, it's much more general, right? It could be anything over here, because everything is an endpoint. Everything can inject. So neighbor-to-neighbor, direct neighbor communication is very simple over here. In fact, this is probably a really good one for direct neighbor or direct neighbor communication, because you have 4 neighbors over here that you can directly communicate with. Whereas here, for your neighbor communication, if you're communicating between 7 to 6, multi-stage logarithmic network doesn't make a lot of sense for that purpose, right? Okay. Let me see. Should we take a break, or should we cover more of topologies? Who wants a break at the moment? Okay, let's take an 8-minute break, and then we'll continue with more topologies. Okay, let's continue. So remember, this is where we left off, talking about a bunch of topologies. And we're going to talk about more. And we're going to start from the other end. Remember, we started with bus and then went to crossbar, well, direct point-to-point, and then crossbar. And then we reduced the cost, actually. But now we're going to go back to the bus. What if you want to actually do better than the bus, but not start with something as complex as a crossbar? And the first thing that comes to mind, if you will, is a ring. Ring looks like this. Basically, each node is connected to exactly 2 other nodes, and nodes form a continuous pathway such that packets can reach any node. So it's essentially a bus that's segmented, where each segment is an endpoint, right? You can think of it that way. The bus is not at a single point, but the endpoints are distributed over this bus. Now you segment the bus. As a result, each link is smaller, shorter, so much more scalable than a bus. So it's cheap because you have n links, but these are point-to-point links between just 2 nodes. So they're not very expensive. And it's high latency, unfortunately, because if you want to communicate from here to the other end of the ring, it takes n nodes. And it turns out it's not easy to scale. And here, bisection bandwidth actually is an interesting metric, because if you keep adding nodes to the ring, you could keep adding nodes. That's not a big problem, actually. So adding nodes is not the problem, but really your bandwidth and latency increase. because your bandwidth is actually constant. If you cut the ring at any point, you're not, by adding nodes, you're not really increasing the bandwidth that you have in the network. And your latency keeps increasing, though, because the number of links that you have between any two nodes is increasing. Your average distance is increasing. Okay. But this is used actually in many chips today because it's actually simple and low cost, right? It's more scalable than a bus. But if you want to actually connect 1,000 things, maybe this is not a very good idea, right? Because now you have, in order to reach from here to here, you need to go 1,000 nodes. Now, of course, that single ring is this is a unidirectional ring in that case. If it's unidirectional, you go only in one direction. So you inject into this node, and it goes only one way. If you make it bidirectional, now you cut the latency in half, right? Which is good. Now, but essentially, you have two rings in that case, right? One in this direction and one in the other direction. So a unidirectional ring looks like this. You have a single directional pathway, and you can see the direction over here. It's simple topology and implementation, and this is the injection path. It's essentially a 2x2 switch still. You can see the crossbar, because one input needs to come from here. It could go into the destination. If this is the destination, it could be ejected out of the network, or it could also be injecting into the network. This is one way of designing the entry point into the ring. It's not the simplest way. You could actually make it simpler. You could do the ejection before the injection, for example, but then your latency may increase and buffering requirements may also increase. But this is one example over here. So it gets reasonable performance if n is small and performance needs are moderately low, right? So if n is small, actually, it's not bad. The cost is On, as you can see, and you get n over 2 average hops. Latency depends on the utilization. Okay. Bidirectional rings essentially means that you don't have only one direction, but you have another direction also. But you can see now things become a little bit more complicated that way. You first need to make a decision. Where do I inject? To the right or to the left, right, when you're injecting? And that determines your characteristics in terms of congestion, for example. But as a result, it reduces latency and improves scalability at this cost, clearly. Okay, so it's obvious, hopefully. And you could make this more scalable by adding hierarchy to it. This is actually true for any network we have discussed. You could add more hierarchy to it, right? You can have a bus connecting 8 nodes, and you could have a ring connecting clusters of 8 nodes, and you could have a mesh connecting that bigger cluster, right? It's possible to actually have a mixed hierarchical topology. I like the idea of hierarchical rings, actually, because each ring is really simple. As you can see, this is a ring over here, another ring, another ring, another ring, and then you have another ring over here that's connecting those rings. And this is another one over here. It's another one over here. So it can get more complicated, clearly. And you could also make these links different amounts of bandwidth, different frequencies, for example, so that if there's more load over here, then this could actually be faster. So there is a lot of design choices over here. And this is a 3-level hierarchy, 64 nodes, for example. But of course, the communication over here is faster. And if you want to communicate from here to here, you need to hop onto this global ring, if you will. And here you can see multiple global rings, and there are multiple endpoints, multiple connection points where you can jump from this ring to this ring, and this ring to this ring, things like that, right? But this gives you more connectivity, as you can see over here, compared to other ones. So you become more scalable by adding these hierarchies, and you hopefully have lower latency, because comparison point is having a single ring connecting all of these. That single ring actually increases latency, whereas if you have this sort of hierarchy, your latency is low here, and hopefully your latency is also low here, right? And you actually end up traversing fewer number of nodes to get from one point to another point. And you could actually optimize even more by mapping your data nicely, if it's possible. You could localize the communication over here. But again, there's nothing magic about it. It could be a bus over here that taps into another ring over here that taps into something else, right? Okay, clearly your complexity also increases. I'm not going to go into the detail of hierarchical networks a lot, but that's definitely one way of scaling things even more. So this is another example of heterogeneity, essentially. And you can read this recent paper that we've done in the past. Okay, but we're going to get back to this mostly bufferless part. Again, buffering is a different choice than topology, and we'll talk about that. So let's look into some other things. So after rings come meshes, actually, logically, if you will. As opposed to being connected to only 2 of your neighbors, now you get connected to 4 of your neighbors. Right. Now this node is connected to 4 of its neighbors. That's not true for the edge nodes, unfortunately. So there's some asymmetry between the edge nodes and the center nodes over here. The edge node is connected to only 2 of the nodes. And we're going to try to fix that problem. The cost is still ON, although the router is more costly here. So here we're talking about the link cost, but the router now becomes more complicated, right? Average latency is square root of n. This is independent of the pattern. And this is easy to lay out on chip. As you can see, it's regular and equal length rings, so it's beautiful. That's why it's actually proposed for many networks that are on chip. And it actually has a lot of path diversity. Path diversity is the notion of having many ways to get from one node to another. From this node to another, you have many, many possible paths, right? So if one path is congested, you could take another path. That's the beauty of this sort of network. Whereas with a ring, you don't have that path diversity, as you can see. You can make it, we have more path diversity by making it more hierarchical, and also by making it more bidirectional. But it's not like this, as you can see, right? This is a lot of path diversity. So this is actually used in many on-chip network prototypes, and people are proposing even more. But think about the router complexity. The router is complex because it's receiving, so this router over here is receiving things from 4 directions, actually 5 directions, because this endpoint is also connected to the router. And it can also send things to 5 other outputs. So it has 5 outputs and 5 inputs. So it's a 5x5 crossbar. So how do you design the router is another thing, of course, right? How do you actually simplify it? We're going to talk about that briefly. Okay, so the problem with mesh, as I said, is it's not symmetric on the edges. So this node doesn't get connected to this node. So the idea of torus, so as a result of this, your performance is actually pretty bad when you're in this edge node. Now you're asymmetric, so your mapping really matters. If you're mapped over here, you can connect, you're very connected. If you're mapped over here, you're not very well connected. Right? So torus gets rid of that sensitivity of placement, sensitivity to placement, by adding another link, basically. Now, if you look at this, this looks like a ring over here, and you have a ring over here, another ring over here. So you basically have rings in all dimensions over here, and all columns and all rows. So essentially, this is the more symmetric version of the mesh. You get higher path diversity as a result, and also higher bisection bandwidth. Again, bisection bandwidth is not the best metric, but if you cut the network, you see 2 more connections, right? Actually, not 2 more connections. You see many, many more connections, right? Okay. But this comes at a higher cost, clearly, and it turns out it's harder to lay out on chip, because this was beautiful, right? This is 2-dimensional exactly. And this is also 2-dimensional, but like, how do you do that, right? Well, I'll show you how to do that. This is one way of doing it. This actually is one dimension of that torus. You're weaving the nodes to make internode latencies almost constant. I mean, one way of doing this is actually, one way of enabling this, you require another metal layer, right? That's not good because that increases your cost now. But with a single metal layer, you actually can do this. But this is a bit expensive. You need to be very careful. Okay, anyway. Let me move to, but there, I mean, we're not going to talk about layouts. That's another design direction in networks, of course. Let's look at, so where do we go after this? The problem with mesh is, I mean, you're connected to only your neighbors over here, right? Your neighbor-to-neighbor communication is very good, but what if you want to reach some other far-away neighbor a lot? Your communication patterns are like that. It takes a long time, actually, with a mesh, right? If you have 1,000 by 1,000, this may not be a good idea, because your distance increases with the square root of n, right? Not good. So how do you actually make things better? Well, torus is one example, but trees are another example. These are now becoming a little bit more specialized now. This enables you to communicate from here to here relatively fast because it's logarithmic on this end and it's logarithmic on this end also, right? It's not square root. And it's still good for local traffic as well at the same time. And it's a planar hierarchical topology that's easy to lay out. In fact, you may have heard of clock trees. Whenever you want to route the clock signal, essentially that's a signal that you need to route to many, many nodes. And you have a network for that also. So this looks like a clock tree to me, H tree, for example. But there are many, many other trees. And latency, as I said, is all log n. And it's good for local traffic, as you can see. If things are local over here, they can communicate with each other through this node over here. And if things are local here, they can communicate with each other with this node over here. And it's cheap, ON cost. It's easy to lay out, as you can see over here, right? It's regular. And you can make things a little bit fat. So fat tree means as you go up higher in the nodes, closer to the root, your bandwidth increases. The assumption is that your communication needs are higher over here because more nodes are connected underneath these higher level nodes. As a result, you want to keep the bandwidth constant, bandwidth per node constant at each level. Make sense? So, of course, this depends on communication pattern. So, actually, the reason fat trees were developed is root could become a bottleneck. So, if you have a single root over here, you may or may not, but you can design it this way as well. But that root becomes a bottleneck. And if you actually have this equal bandwidth at all levels, so the bandwidth at this level is equal to the sum of the bandwidth link bands at this level, equal to the sum of the link bands at this level, then you avoid that problem, assuming if your communication is all random and uniform, then hopefully your root doesn't become a bottleneck in that case. Make sense? Hopefully that's clear. So fat trees were first developed in the Connection Machine 5, which is a parallel computer, which unfortunately we didn't get a chance to cover in more detail, but maybe we'll have a parallel architecture course at some point that's even beyond this. Okay, so a fat tree example, this is Connection Machine's fat tree, and that's a nice paper that describes Connection Machine, at least the fifth one. The earlier Connection Machines, actually, Connection Machine 1, was designed to be very, very parallel. It's a supercomputer, essentially. But basically, they designed it to be bit parallel. And the idea is there's so much parallelism in the workload that they were doing that they had, I think, 64,000 nodes, where each node had a bit serial adder. So this is actually, if you think about some of the things that we've discussed in this course, like Ambit, if you remember, where we did bitwise computation. Those are not necessarily new at the computation level because people thought, oh, we have a lot of parallelism. Why do we need adders that are complex? We just do bit serial addition. We just do 64,000 of them at the same time. And they had a connection that looked, well, this is CM5, so I don't want to confuse the different things. This is the fifth version of it. But they had connections like this in the CM5 version of this. And they did a lot of things, as you can see over here, right? They did randomized routing going from to the top so that they could minimize congestion. So if you want to transmit from here to here, you randomly select one of the top nodes over here. You could select this one randomly. And then once you go here, you could select this one randomly. And once you go here, well, maybe you don't do random selection because you have a destination over there. Okay? So that reduces your congestion over here. And they did combining operations like we've discussed, fetch and add, multicast, and reduction operations. Basically, they did addition over the network. So if you think about it, what is a tree good for? If your pattern is like that, let's say you're doing additions of many, many numbers. Each of these nodes does a single addition and passes the result up. And this node does an addition, pass the result up. This node does an addition, pass the result up. Eventually, you have the result at the top of the tree, right? So you can actually map a lot of additions beautifully onto this network. So your computation can be mapped to this network also. So some of the computation patterns are extremely efficient in these networks, whereas they may be extremely inefficient in a mesh type of network, actually. Okay. That's all I want to say about CM5 and the fat tree. But this is an example of a fat tree, as you can see. And it gets connected to other stuff also, which we're not going to talk about. Okay, let's be a little bit more complicated. So this is actually a hypercube. Now we can see that there are many, many other possibilities, and we're not going to treat them theoretically. Basically, it's an n-dimensional cube or n-cube, and you can see the progression over here. This is a cube, and this is the 4-dimensional cube over here. But the characteristics are kind of nice. You get log n latency, similar to trees. You get log n radix, a little bit more than trees. And your links grow with n log n. So it's not as bad as a crossbar, clearly. And some communication patterns may fit nicely to it. It's low latency because of the log n characteristic. One downside is, how do you lay this out? I'll give you an example of the 64 node version of this in a little bit. And that's it, basically. I think this is a 64 node version. It was developed in 1984 at Caltech, the Cosmic Cube. It was the first known message passing machine. Actually, this is a beautiful paper that I would otherwise assign. But maybe we can put it as not a required reading, but yeah. But you can see this is how they connect it. And you can read this over here. A hypercube connects n equals 2 to the small computers called nodes through point-to-point communication channels on the Cosmic Cube. Shown here is a 2-dimensional projection of a 6-dimensional hypercube or binary 6 cube, which corresponds to a 64-node machine. And this is another view of it over here, smaller dimensions, as you can see. But basically, you can analyze the characteristics. Communication patterns matter, clearly, and you can read the paper for more detail. I'm not going to go over this more. So you have a lot of freedom in designing networks, as you can see. And this was designed mainly for low latency messaging, but it may or may not be good for all communication patterns. Any questions? No? You have your own topology in mind right now? Maybe? Okay, topology is actually not an easy topic these days, but there's still a lot of innovation that needs to happen in that domain. But usually the innovations, I think, require not just topology. Like we've been discussing in this course, right? There's no single shot that you have. Maybe you come up with a great topology. It usually comes at the expense of something else, like routing. Your router becomes more complicated, for example. So you need to really design the entire system to be balanced and energy efficient, cost efficient in the end. Let's talk about routing. We're going really slowly. Okay, so hopefully we'll have some time to discuss what to do next week. Otherwise, we're going to do this next week. Okay, so routing mechanism. There are a lot of options here. Mechanism could be arithmetic, meaning you do simple arithmetic to determine the route. And this is usually good for regular topology. And I'll show you an example of this. In a mesh or in a torus, or tori, you can do dimension order routing, which is basically, you say the next node, if I'm the source and the destination, to go from the source to the destination, I'm going to first traverse the x-axis. And then once I get to the y-axis of the destination, I'm going to traverse the y-axis. I can easily do the routing by arithmetic operations very simply by subtracting x from y, by getting the Euclidean distance, right, of those two things. Okay, but actually by getting pairwise x and pairwise y distances. You don't even need the Euclidean distance. Okay, so or you could do it source-based. Source specifies the output port for each switch in the route. That's one way of doing it. Basically, you basically figure out how do you go from the source to the destination, and source specifies it. Or you can have a table lookup-based routing. You index into a table for the output port. And if you're doing packet-based switching in the router, it's usually how this is done. But it could also be done in some other ways. Okay, you have simple switches in this case, no control state, and you have a large header because you do source routing, right? Source specifies all of the routes that you're going to take downstream. If you're going through 1,000 routers, well, good luck. You have a huge header specifying all of that. So this is actually not so scalable. This is more scalable. You have a small header, but now your switches become more complex. Right? Your routers become more complex. Okay, there's also algorithm. This is mechanism, as I said, and there's an algorithm for routing. There are 3 types in general. It could be deterministic, meaning given the same input, you're going to choose always the same output. You always choose the same path for a communicating source-destination pair. It could be oblivious, meaning you choose different paths without considering the state of the network, oblivious to the state of the network. It could be adaptive. You could choose different paths from a source to destination, adapting to the state of the network. So clearly, your performance usually increases as you go from here to here. But again, it's dependent on your communication pattern as well. So how do you adapt is another question. You could actually look at local or global feedback. What is the congestion in the next router, this output port over here, versus what is the congestion in this general area that I'm going towards? Right. That's more global, perhaps. And you could also, you have a decision. Do you always go through the minimal path, or do you sometimes take non-minimal paths? Minimal path is the minimal distance, right? Sometimes you may be better off taking non-minimal paths if the minimal path is congested, right? If you're going to be delayed on the minimal path. Because this is minimal without considering congestion. Okay. So let's look at the deterministic routing. Here, all packets between the same source-destination pair take the same path. Dimension order routing, as I already said. First traverse X dimension, and then traverse the Y dimension. This is first used in Crate T3D and many on-chip networks today. This is called XY routing also. You could do the opposite also, YX routing. Okay, it's simple, clearly. You can do simple calculations to determine which way you go first. It's deadlock-free. We're going to talk about this in a little bit. This is actually a big concern in a routing algorithm if you're designing a system. You want to ensure there's no deadlock in the system, right? And it's dangerous if you have a deadlock, then your system doesn't work. So there are a lot of correctness issues over here. There should be no cycles in resource allocation. I'll give you an example of this in a little bit. It's deadlock-free because it limits the turns that each packet can take in this case. You can only take some turns, right? Whenever you're switching between X and Y, you take that turn. And everybody takes those turns, which means that you're never going to have a cycle in the resource allocation requirements of different packets. If everybody's always going from X and Y to go to destinations, they're not going to require the buffers in a cyclic manner. That's basically the insight of this. Whereas if you actually did XY routing, and also you were able to do some other path the other way around, you could turn the other way around, and everybody can turn the other way around. As a result, you could have a cyclic resource allocation. The downside of this is it's limiting now your choices, right? To go from this node to this node, you always go this way, right? You cannot go this way, because that would be YX routing. Or you cannot go any other way, right, in between. So this is actually restrictive. It's deadlock-free, but it's not the best deadlock-free algorithm, because you could actually be deadlock-free without being this restrictive. And because, it's not the best because it doesn't exploit that path diversity that I just showed you pictorially over here. Okay, so what is deadlock? Deadlock means no forward progress. It's caused by circular dependencies on resources. In this case, each packet, for example, waits for a buffer occupied by another packet downstream. So this example over here shows a deadlock. This packet 3 wants to go this way because this is the output port that it needs to take, but it's occupied by packet 4, as you can see over here. This packet 4 needs to go this way, but this output port is currently occupied by packet 1. This packet 1 needs to go this way, but this output port is currently occupied by packet 2. And this packet 2 needs to go this way, but this output port, where packet 3 is occupied. So clearly you have a cyclic dependence because all of the packets are waiting for each other because you didn't consider this in your routing, essentially. If you did XY routing, this wouldn't happen, and you can prove that it doesn't happen. But I'm not going to do that. If you really want to do that, you can do it yourself or read a paper that I'm going to talk about next slide. So how do you solve this problem? This is a general problem. And there are many solutions you can come up with, like everything in computer architecture. One is avoiding cycles in routing, as I just said. Basically, you do the routing such that you never get into such a situation. And you could do it by restricting the turns each packet can take. Or you could avoid deadlock by adding more buffering, escape paths. So you could say, okay, my algorithm is not deadlock-free, but I'm going to add a lot of buffering such that it doesn't happen. That's a possibility. You could design the mechanism such that it's deadlock-free, even though algorithm may not be deadlock-free. Right? And one other thing is, this is called escape paths, for example. You could have another buffer over here where you can escape to if this happens, right? And if you have enough buffering, and if you have conditions where you can really escape somewhere, then that's good, right? You will run into the situation, perhaps, but you will avoid it by utilizing these buffers that you have. Now, the question always comes, what if you run out of all of those buffers? Right? So you need to guarantee that you don't run out of those buffers, or at least you have some action plan if you run out of those buffers, right? One action plan could be you detect and break the deadlock. This is usually a tough problem. Actually, people try to. Actually, these things exist in synchronization and multiprocessors as well, right? Because you're trying to get a lock, and how do you avoid deadlock in that case? And people have proposed mechanisms for this. For example, you could preempt the buffers. You could say in this case, oh, I detected the like lock. I'm going to throw away this packet and ask the sender to resend it. That's one way. Okay, so clearly there are a lot of choices, and there's different levels of complexity over here. It's good to have an algorithm that doesn't run into these situations in general. And this paper is the paper that talks about how to not run into it. It's a seminal paper, which basically suggests that you should analyze the directions in which packets can turn in the network and determine the cycles that such turns can form and prohibit just enough turns to break the possible cycles. If you do that, you're deadlock-free, and read the paper for more detail. I'm not going to go through that. But XY routing, for example, is deadlock-free, but it's not the most optimal deadlock-free algorithm in terms of performance. Okay, let's look at some other algorithms for routing. Any questions, by the way? Deadlock freedom? I just went over a huge topic very quickly. That's fine. Okay, let's look at some other algorithm. We looked at deterministic algorithms, right? There's another algorithm that's oblivious, and this is a beautiful algorithm by Leslie Valiant. It's called Valiant's algorithm. And the goal over here was to balance the network load. And the idea is very simple. If you want to go from the source destination to a source location to a source node to a destination node, you first choose an intermediate node randomly, and you first route there with deterministic routing, let's say. And then from that intermediate node, you route to the destination node, again, let's say deterministically. This way you avoid deadlock, but you hopefully balance the network load by choosing this intermediate node randomly across the network. Okay, I said that. So this randomizes and balances network load. If that's the goal, that's good. If your communication patterns are random, uniform, this may be good actually. It's non-minimal, clearly, by definition, because you're randomly choosing a destination node. It could be actually far away from the destination. Intermediate node. It could be actually your destination. It can be right next to you, and you may be doing this. That's probably not a good idea in that case. Which means that you should probably optimize it. So you may want to do this only when the network is highly loaded. So when do you want to balance the load? Your communication patterns should be such a way that your network is highly loaded, and maybe you don't really care about the distances you take, right? That's possible, right? Because your communication patterns may already be random to begin with. Or you could restrict the intermediate node to be closed, right, in the same quadrant. Or you could make this communication pattern aware. So you could do many, many optimizations in this case. But the key question is, when do you really want to balance the network load? So this goes against latency. But this utilizes, so what this really helps is link utilization, right? It utilizes your links really well. Again, that's not always true, right? If your communication pattern is always nearest neighbor, you always communicate with the neighbor next to you. Doing this is actually pretty stupid, right? You don't want to do this. You don't want to go farther away to just get back to your neighbor. Okay, so your communication pattern is extremely important, basically, in your routing algorithm. Okay, so adaptive routing is the next step, basically. You could actually make this adaptive also. Right now I said it's oblivious, but if you try to make it congestion aware, communication pattern aware, now you're becoming adaptive. But adaptive means usually adaptive to the network state. There are two types of adaptive. Minimal adaptive. In this case, router uses the network state to pick which productive output port to send a packet to. So minimal means you always take the minimal path, right? Which means that at every router, if you're packet switching, or even if you're circuit switching, you have a choice. And your choice, you should always choose the minimal, meaning productive output port. What is the minimal what is a productive output port? It's called productive because it always reduces your distance to the destination. Well, I said that over here, basically. Non-minimal is different. Basically, you can choose non-productive output ports, which means that you could actually, well, a productive output port is either it reduces your distance to the destination or it doesn't change it. Although you should always choose the one that, if you're really doing minimal routing, you should always choose the one that's productive, that reduces your destination, right? actually, I'll change that, because if it doesn't change your destination, if it doesn't change your distance to the destination, you're basically staying at that router, right? Is that true? You can move to some other router and your distance still may not change, depending on your connectivity in the network. So don't assume connectivity. So that's also possible. Okay, anyway, let's ignore that. In this case, non-minimal means you basically misroute the packets to some non-productive output port that takes you away from the destination, right? And you could do that based on network state, right? It's also called fully adaptive. So the upside of this is you can be aware of the local congestion, but this minimality restricts achievable link utilization, right? Basically, you always need to pick between productive output ports. Maybe you have only one choice in the productive output port, right? If you have a mesh network and you're going toward, let's say your source is here and your destination is here, how many productive output ports do you have in this router? Only one, right? Because wherever else you go down, you go up, you become non-minimal. Okay, so minimality, actually, so we'll talk about why minimal is nice when we talk about the negative downsides of this, right? Actually, what is the downside of this? If you're going away from your destination, there's a big downside. It's related to correctness. How do you guarantee that you reach your destination, right? There's a problem here, actually. That's why people like minimal routing. But minimal routing reduces your link utilization. Non-minimal routing, you can achieve better link utilization on load balance because now you're actually exploiting all of that path diversity. You're saying, oh, this path is minimal, but I'm not going to take it because there's a lot of congestion over there. I'm going to go around the network and go here. It's just like roads, right? Going from Zürich to Lausanne, you may actually take the direct path, but if that's congested, you say, I'm not stupid, I'm going to go some other route, right? That's maybe 1 hour slower if you don't consider that congestion. So it's obvious. But you'd better get to your destination. So you need to do the routing such that you guarantee live lock freedom. I think that's the problem with the non-minimal adaptive algorithms. So you need to have a mechanism that's implemented such that you don't keep circling around in the network. So how do you do that? Well, one way is ensuring that the router is always prioritize the packets in some total order. So whenever you inject the packets into the network, they're automatically assigned a total order, and the router always obeys that total order. As a result, every packet gets to its destination in that order, which means that the oldest packet in the network based on that total order always gets routed minimally, right? You just need to ensure that one packet gets routed minimally, and that happens in a total order, right? That's the minimum condition, actually, for being live lock free while being fully adaptive. The downside is this makes the router more complex now because you need to obey that total order. And I'm not going to go into it. There are ways of actually reducing that complexity, but if we have time, we'll talk about some of those ways. Okay, so adaptive routing has other beauties. You can, for example, avoid faulty links and routers. If you have XY routing, you're not aware of that, right? If a link becomes faulty, well, too bad. I only have XY routing, and I hard-coded this routing algorithm into my router. The only way you can fix that problem is by replacing your router and replacing the faulty link with something. That may not work, right? But adaptive routing enables you to route around faults, right? You can easily say, oh, I'm faulty, so don't route to me. And the router clearly says, okay, I'm not going to route toward this output port. And the algorithm is clearly adaptive because it already was designed to be adaptive. As a result, you could avoid these faults. So there are benefits to adaptive routing. But of course, the live lock is an issue. And actually, deadlock is an issue also over here too, but we also already talked about that, right? So deadlock and live lock are both issues over here. Okay. But you could turn the deadlock problem into a live lock problem. Very briefly, I'll talk about that as well. But deadlock means that you have a resource that's not available, right? If you always misroute, you'll never deadlock, really. Right? You can always escape to some other output port. The only thing you need to guarantee is you need an output port that's free to escape to. And that's easy because that you can guarantee by topology, right? if the number of input ports is less than or equal to the number of output ports, you are already guaranteeing that you can misroute any packet that you're receiving. Right? Okay? So we've turned the deadlock problem into a live lock problem in this case. And hopefully live lock problem is easier to solve. And it gets you the benefit of adaptive routing. Okay, so basically deterministic routing cannot handle these faulty components. That's the upside of adaptive routing. But if you have adaptive routing, now you need to change the routing table to disable faulty routes. Assuming you can detect the faulty link on router, of course, right? Somebody needs to do that detection. And this ties into what we've discussed yesterday briefly in reliable systems. And this is important, actually, but this is an easy thing to do. Okay, so adaptivity is in general good for fault tolerance, as you can see over here. We talked about adaptivity from the performance perspective, but it's also good for fault tolerance. And you can read this recent paper that we've done, which I like, because it used a lot of different concepts to actually guarantee delivery when you have faults. And it's also fully distributed and low overhead. But there's a lot of work in this area. Okay, let's talk about buffering and flow control a little bit. So we've covered, what have we covered? We've covered topology, we've covered routing, and now buffering and flow control. So we're going really fast, but really slow. Any questions so far? That's the minimal path routing problem. That's a deterministic one, yes, sure. I mean, certainly any kind of routing algorithm could be employed in anything, but Dijkstra's routing is more theoretical. It's basically on a graph, essentially. Yeah, but let's not talk about that here. There are many, many routing algorithms. Okay, so recall circuit versus packet switching. Remember, this was by nature bufferless, and this was by nature buffered, right? So your choice at the very high level can also help you with what's happening at the buffering, right? So implicitly, I think you're making a choice with buffering over here. Or if you don't have buffering, maybe this is a good choice. So think about the interactions to begin with. So let me give you a little bit more. This is boring again, I think, but you need to have stuff. So what gets stored in the buffers is always a question, right? Well, what gets stored is you need to have a header in a packet that controls the routing and control information. Your payload carries the data. And it can be further divided into many, many things, ... And you may have an error code also, so that the receiver checks whether the data is received correctly, right, without transmission errors. We haven't talked about that, but there's certainly a lot of redundancy built in to these networks. So this could be a checksum, for example. It could be the CRC, and it's usually appended to the end because you actually compute it as it goes along, right? Okay, so this is what gets stored in buffers. We're going to talk about buffers more, but let's be a little bit more fundamental. The key question we're asking with buffering and flow control is how do you handle contention, really? If you don't have contention, buffering and flow control is not really important, in my opinion. I mean, you may need buffers for other reasons, like to actually inject into the network. So the buffering is beneficial, clearly, whenever you're switching from a high throughput thing to a low throughput thing, right? If buffering enables you actually to ensure that this high throughput thing can make progress while the low throughput thing actually is generating answers. So there's another reason for buffering, clearly, but we're not going to talk about that here. We're going to talk about the buffering that you have inside the router over here. So you have two packets, or flits. They're trying to use the same link at the same time. They want the same output port. What do you do? And there are three fundamental choices over here. One is clearly buffer one and send the other one on the link. What else? Give me the two other ones. I'll do what Subbus did and not progress. And next week's beautiful lectures will be gotten. There you go. Drop one, perfect. Yes, you drop one. Now you're adding some different kind of complexity because you need to notify the sender. I dropped your packet, please resend it, right? Which means that you generate another packet to send to the sender. What happens to that? You need to buffer those, probably. You need to ensure that the receiver receives them, yes?
Maybe you could have a timer or something if there's no acknowledgement.
That's right, yes, exactly. That's another thing, right? So even that one has choices, basically, right? Do Once you drop, do you negative acknowledge, meaning you've dropped it and the sender should send it again? Or the sender infers the fact that it may have been dropped and resends it. Now, they may be correct or incorrect. Or you could have a mathematical formula where the sender actually, says, clearly I should have received this packet, theoretically. This is the theoretical maximum I should wait for. But then that may be a huge theoretical maximum, right? So there are clearly trade-offs. What about the third one? I promised you a third one. Exactly, use another path. Misroute one. That's called deflection also. Basically, if there's some other path, some other output port, you assign that output port. And these three are fundamental. I don't think there's another one. So clearly, if you use another output port, now we're non-minimal adaptive. Right? Well, you could use a productive output port. Two output ports can be productive at any given point, clearly. Because if your destination is here, both this is productive and this is productive. So first, you could use a productive one, but that's not misrouting. That means that this packet has a choice. It could take either this one or this one. It's still minimal in that case. So that's fine in that case. But misrouting really says that, this packet goes toward a direction that it really should not go to minimize the path to the destination. Okay, so clearly there are trade-offs, and we're going to look at some of these trade-offs over here. So this way you can get rid of all buffers. Right? There are no buffers now. This way you can get rid of all the buffers also, but there's some more complexity. Here, the problem of live lock freedom comes into play, right? And how do you actually misroute one? How do you design a router? So all of these have implications on the router design internally, and also the protocol design. And let's see. Okay, we're going to see some flow control methods. Circuit switching, we've already seen. Bufferless, I'll call this in general. These could be packet or flit-based. And we're going to see a bunch of buffered flow control methods. We're not going to spend a lot of time. I have some slides at the end that talks about bufferless. Actually, bufferless, this dropping was first proposed for the internet, actually much before internet, distributed communication networks in general. Paul Baran has a seminal paper on this. It's also called hot potato routing. And the reason is the packet is a potato. It's hot. You cannot keep it. It's too hot. So you send it to someone else quickly. And someone else doesn't matter. Just send it to someone, right? And it was when internet was first being developed, it was proposed for the internet, and people said, this is a really good algorithm. But there are downsides to this also. If your load is really high, you have a lot of hot potatoes circulating around in the network. So it actually doesn't perform really well at high loads. Remember the load latency curve that I drew a long time ago in class? We're going to see that again later on. If you are doing misrouting or deflection for every packet, then your latency shoots up very quickly at low load. So this is really good for low loads. If you think about this, if you're misrouting, you don't have buffers, but you're utilizing the links as buffers. You'd better have some free links. When do you have free links? When somebody else is not injecting into the network, when your load is low. Okay, so we're going to see a bunch of buffered flow control also. Okay, let's start with this circuit switching, revisit it. Circuit switching is interesting. The idea, again, is pre-allocate the resource across multiple switches for a given flow, more formally. You need to send a probe to set up the path for pre-allocation, as we said. And we said resource allocation is granularity is very, very large, right? Because you're really allocating the resources, routers, right? Or actually, at least output ports in routers. So nobody else can use them. There's no need for buffering, no contention. The flow's performance is isolated. It can handle arbitrary message sizes, but it's not good for small message sizes, as we discussed. You get lower link utilization because two flows cannot use the same link at the same time. It's dedicated to one flow. And you have handshake overhead to set up a circuit, which really kills the idea for really small flows. If you have large flows, it's a good idea. So it makes sense to actually incorporate circuit switching into your system, even if you have buffers, because you reduce the dynamic switching overhead as we've discussed, right? Okay, bufferless routing. This is the paper that I mentioned by Paul Baran from 1962. The idea is, again, that packets are never buffered in the network. When two packets contend for the same link, one is deflected. So it's a beautiful idea, actually. If these two packets need to go to the same destination over here, they arrive at this router at the same time. And this router says, I'm going to prioritize the red one for some reason, hopefully based on some total order such that you avoid the live lock in the system. and this one reaches its destination in one cycle. The other one takes the scenic path. So it sees more routers, essentially. Now, it's clearly not minimal. It's also not low latency, because you could have buffered the blue one, and after one cycle, at this point, it would have reached its destination, right? But it didn't, because it took the scenic path, the longer path. So it arrives after a while. But you got rid of the buffering over here. Okay, and you inject new traffic only when there's a free output link. So you have an endpoint over here injecting into the network. It needs to detect when it can inject, clearly. So injection becomes a little bit more complicated, but you have that problem in a buffered router also. Okay, so basically, this is at a high level, high granularity, what a buffered router looks like. You can have input buffers, you can have output buffers, you can have both, actually. And people try to optimize these buffers a lot. And you have different characteristics in terms of allocation. So clearly, you have a switch over here, right? But you need to arbitrate. And you need to arbitrate based on some priority over here. Do the oldest first, round robin. We're going to talk about those at the high level. So there's a lot of complexity over here, actually. And we're going to see something like do you have multiple different buffers coming from the north side over here? So this could actually be very complex in the end. So if you have bufferless deflection routing, you can get rid of these buffers, basically. Right? It looks a little bit beautiful over here. But it's not as beautiful because this deflection routing logic is actually more complex potentially more complex than the other logic that we've discussed. And you need to actually design this well. So this is your required reading that doesn't talk about this complexity over here. So it's optimistic. It's proposing the big high-level idea, but there are later papers that actually optimize this deflection routing logic. Okay, so that's the basically key idea. The packets are buffered in the pipeline latches that you have, which is not shown here. Clearly, this is a pipeline router. If you want to make it high frequency, you actually need to pipeline the routing logic also, which we will briefly talk about, and also network links. Okay, so there are issues in bufferless deflection routing, live lock, router complexity, and performance and congestion at high loads. If you're really interested in this, we have written a book chapter that covers a lot of these issues and the state of the art in research in this one. But there is a lot of potential research in this area going forward, in my opinion, because this is really has a lot of a really good implication on energy efficiency going forward. Okay, that's all I want to say about bufferless routing for now. Now let's switch to what people have done for a long time, and that's really buffered routing. And buffered routing actually can take a lot of shapes. So I'll talk about store and forward. In this case, flow control. Remember, flow control determines when you can move a packet at some level. It could be packet-based. Store and forward says it's packet-based. Basically, you need to receive the full packet before you can send it somewhere else. That's why it's called store the packet and forward it. The flow control unit is the entire packet. Basically, packet is the flit. Packet size and the flit size are the same in this case. And so this leads to high per packet latency, as I will show you. And it also requires buffering for entire packet in each node. So your buffering requirements go up because you have to wait for the entire packet. So if a packet is 256 bytes, a response, for example, to a cache block request, you need to wait for all 256 bytes. And once that's done, you send all 256 bytes here. Once that's done, you send all 256 bytes here, ... This doesn't mean that your links have to be 256 bytes. Your links can be actually 1 bit. You take 256 cycles to actually send those 256 times 5, 256 times 8 cycles to send all of those. And this router needs to wait for all of those to be sent before it sends a single bit from this packet over here. That's stupid. But it's been employed. That's basically what's happening. Right? You wait for the entire packet to be received before sending it over here. So packet-based flow control. But can we do better? And of course we can do better. You can actually do something like cut-through. You start forwarding as soon as the header is received and the resources, buffer and channel, for example, are allocated. So you get huge reduction in latency over here. And you can still allocate buffers and channel bandwidth for full packets. So that doesn't reduce your buffering requirements, but reduces your latency. So if you look at, I don't know why it's not animating. This should be animated later than that one. So maybe you can remind me. So basically, this is what's happening right now. Now some of your packet, some part of your packet is actually arriving earlier. because it's really cutting through the network over here, the routers. Okay, this is obvious. I think you can play with it. The problem is if packets are large, this doesn't reduce your buffering requirements significantly. Right? Basically, what to do if your output port is blocked. So it lets the tail continue when the head is blocked, absorbing the whole message into a single switch. Basically, you're back to a large buffer to hold the largest packet if your output port is blocked, if somebody else is using your output port. So at contention, when you have contention, this doesn't work as nicely. So you're back to square one, meaning store and forward. Okay, so can we do better is the question. And the better is essentially wormhole flow control. In this case, you break the packet into smaller flits. Now this becomes your buffer as well as bandwidth allocation unit. So your packet is large, but your allocation unit in your buffers is much smaller. It's called a flit. And there is a specific way of these things being sent across the fabric, and they're like a worm. Worm has a head, worm has a body, and worm has a tail. And the head sets up the output, and the body and the tail follow. And the tail deallocates the output port. So the only arbitration that you need to do is for the heads of worms. Right? So if you have two different heads that are contending for the output port, one of the heads gets chosen by the router and gets allocated the output port, and that output port gets allocated until the worm goes, and the output port gets allocated to, once the tail of the worm comes, it deallocates the output port such that another worm can use that output port. Make sense? But this happens at a very fine granularity. So this is the head, for example. This head is allocated this part, this part, this part. All those output ports are allocated. In a sense, it's circuit switching at a worm level, right? That's essentially what's happening, actually. You're allocating this output port at a worm level. And you don't have the handshaking overhead of circuit switching, because this head is the thing that allocates it over here, saying, I have a body and a tail following me. Okay? So that's the beauty of this wormhole routing, I think. It's circuit switching at a very fine-grained level. Okay. As you can see, now your buffering requirements are much lower because you're buffering these flits. And, okay, that's good. So body follows the head, tail follows the body. It's pipelined. If head is blocked, the rest of the packet stops. And routing information is only in the head. So how does the body tail know where to go? It's circuit switched. So head leaves a message saying, oh, this is allocated to the body. It's beautiful, right? And latency now is almost independent of the distance for long messages, right? Because you're really pipelining it over the entire network. Because your latency is really dependent on how fast you can switch every single flit. You're not waiting for the entire packet to arrive. You're really doing the sending this little fine-grained portion of each packet. Okay, so the advantages over store and forward flow control are huge. You get a lot lower latency and much more efficient buffer utilization also, because you're never waiting for the entire packet to be buffered. But there are some limitations still, and we're going to talk about those. It suffers from head-of-line blocking, and I'm going to show you an example of this. So basically, if the head flit cannot move due to contention, another worm cannot proceed, even though the links might be idle. And let's take a look at an example of this. Let's say we have these two input queues over here, and there's these two outputs over here. I'm going to show you a better example, actually, over here. But you're receiving inputs from 1 and 2. And both of these input queues have packets that need to go toward this direction. Right? So both of these want to go through 1. Now, this gets selected. This little thing needs to go through 1 over here. But this one wants to go to 2, but it cannot go, right? So if you look at the input queues, they both have head of worms that need to go through the output port 1. The router, for some reason, selects this one. It says this cannot go. But this cannot go because it's blocked behind this one that's allocated this port. And this cannot go because it's blocked behind this one. That cannot go because it's conflicted with another one that's get allocated to the same port. Now what happened is, because these are queues, they're FIFO queues, whatever is at the head of line blocked the next one, even though the output port, the next one requesting is unallocated. Make sense? Well, why does this happen? This fundamentally happens because it's a queue. It's FIFO, right? Actually, all of the principles that we've discussed, out-of-order execution, for example, can be applied here. You could allocate, you could make arbitration a lot more complex and say, I'm not just going to look at the head of queues, I'm going to look at everything in the queue. And if you looked at everything in the queue as an arbiter, you could say, oh, this is requesting 2, so let me send that over here. Now, you could do that. Now it gives you a lot more complexity now, right? Head of the queue, checking the head of, checking 2 things is a lot easier than checking 2 times n things, where n is the size of your buffer. That's why a lot of routers actually do not do this. There's no reason not to do this except for complexity and cost. Okay, make sense? Okay, I'm not going to take another break, if that's okay. We'll finish it, and then we'll talk about some things. Okay, so a worm can be before another one in the router input buffer. Due to the FIFO nature of the input buffer, the second worm cannot be scheduled, even though it may need to access another output port. That's basically head-of-line blocking over here. Let me show this to you pictorially. So if you look over here, this is for some reason blocked by other packets. You have this blue packet. Blue packets cannot go here because the buffer is full. It cannot proceed, but there are some other packets that are happening over here. Now this blue packet is requesting this output port, but it cannot go because the buffer downstream is full, but it has blocked the red one, which is trying to go here. It's kind of bad, right? You have an empty link over here, unutilized link, but it cannot be utilized because you have a queue that's FIFO. Makes no sense, actually, if you think about it, but you designed it to be simple. That's why it's this way, yes? Yeah. Yeah. So even if you use, this is pictorial actually, this is assuming one queue, but even if you use per output port queue, the same problem can exist, right? Think about it. Let me continue. Maybe you'll have your question again, right? Yeah, okay. You can do the nearest neighbor communication to see how So basically, red, if you look at this I'll cover it, and if your question still arises, we can look at it. So red holds this channel, and this channel remains idle until the read proceeds over here. So the idea is essentially using multiple queues. So if you look at the input ports over here, you have these queues. And basically, you have a single queue per input port. Maybe your suggestion was actually having multiple queues for a single queue per output port, right? Anyway, let's go back. So let me give you the key idea, and then if the question still arises, we'll get back to it. But basically, the idea is you have one physical channel over here. The problem is really this FIFO queue. One solution is, as I said, do out-of-order scheduling out of this FIFO queue and pick the one that's not blocked, right? That's certainly possible. So the reason, okay, let me go back because I think your question is very fundamental. There might be a misunderstanding here. So you have you have some flits over here. Let's say this one is requesting this output port, and this one is also requesting this output port, and you have this one requesting this output port. Right? If this one gets allocated this output port, the second one over here will be blocked because this one doesn't get allocated this output port. As a result, even though this is going to a totally separate output port, you'll be blocked. Right? Does that make sense? Even though you have different queues over here, you'll be blocked. So really, you really need to have multiple queues, as you can see over here. And the idea is divide up the input buffer into multiple buffers sharing a single physical channel. It's a very simple idea, actually. This says basically, instead of having a single FIFO queue, have multiple FIFO queues and arbitrate with the heads of those. This reduces head-of-line blocking. It's not as good as out-of-order scheduling, right? Because out-of-order scheduling looks at every single packet over here, so you could do much better than that. But now you keep the FIFO-Q nature of the thing. So clearly there's a space of optimization over here. Is out of order better, or is having multiple queues better? I'm not going to go through this actually. This debate actually has appeared in processor design as well. Processor design has come the other way. We have these huge out of order selection logic inside the processor. How do we simplify it? Now, network folks have a similar problem actually. They started with a really simple, stupid design, which is a single FIFO queue. And they saw that, oh, you have a lot of blocking in this because you have a lot of independent operations. How do you figure out those independent operations and send them to output ports? Well, add more queues. Actually, out-of-order design, if you look at an out-of-order design today, it consists of a lot of queues. And actually, it arbitrates between those queues. One of the, if we had time, we would actually discuss that. But one of the ways of reducing the scheduling window size and scheduling window complexity of an out-of-order design is to break it down into queues and arbitrate among the heads of those queues only. Does that make sense? So essentially, there's a very similar design choice that's over here. But these are called essentially virtual channels. Maybe it's an unfortunate name. I'm not sure why this is virtual, actually. But really, you have 2 FIFO queues as opposed to 1. And this is actually from the paper, the seminal paper that introduced the idea. As opposed to having 16 FLIT FIFO buffers that look like this, you have 4 lane or 4 virtual channel FIFO buffers where each of them can hold 4. But now you can schedule potentially one of the 4 over here, as opposed to scheduling only the head. So head of line blocking reduces because there are 4 heads here as opposed to a single head. Right? It's a very simple idea in the end. Okay, so let's look at this again. So I assume that this is blocked by other packets here. You have this blue one. The blue cannot proceed because the buffer is full. But now, because you have 2 virtual channels over here, the red can go to some other virtual channel. Right? And it can proceed. Make sense? Okay. The reason that was happening is you have a shared input buffer, right? The input buffer coming from this, I guess, what is this? This is west, right? Yeah, coming from the west is shared between these 2. Now, actually, you have 2 different input buffers coming from the west. Okay, so a modern virtual channel-based router looks like this. Basically, you have an input channel, and they go to these different virtual channel buffers. As opposed to having a single one over here, you have V of them in this case, right? And then they all arbitrate for their output ports. And there's this, so there's this switch allocator. There's a virtual channel allocator for the next one, next router actually. Because whenever you actually send the FLIT downstream from the previous router, you need to actually figure out where to allocate it. And that happens actually in the previous router. These routers need to communicate with each other. So you take the virtual channel identifier and you buffer it immediately, because you need to know which buffer to go into in the previous router. That's why actually virtual channel identifier is part of the packet that's coming in, or FLIT that's coming in. And then you get assigned, and these arbitrate for the output ports, which may be all different. And then this, one of them gets allocated an output port over here, assuming someone else doesn't get allocated the same output port, right? And that's done by the switch allocator over here. And at the same time, while this is happening, the one that gets allocated a virtual channel as well in the downstream router, so that it knows exactly which buffer it needs to go to in the next router. So now you can see the buffering actually becomes complicated and complicated, right? Okay. So virtual channels are actually useful for other reasons also. Deadlock avoidance is one that we've discussed. You can actually enforce switching to a different set of virtual channels on some turns, and you can break the cyclic dependency of resources. You can always say, oh, you go this way, because otherwise I will run into deadlock. That's a possibility. And this can happen by enforcing some order on virtual channels, but I'm not going to go into that detail. You could also have escape virtual channels, have at least one virtual channel that uses the deadlock-free routing. Now you're complicating a lot of things, clearly. And ensure each FLIT has fair access to that virtual channel. By the way, I didn't talk about the router in detail, but there's clearly routing logic over here as well, right? Somebody needs to determine where you need to go. Based on that, you need to determine which output channel you get, And again, based on that, you determine which virtual channel you get allocated. So there's actually a lot of sequential dependence in this computation, and people optimize that sequential dependence by making it more parallel and making it more speculative. Actually, there's a lot of speculation that's employed in the routers. You assume that you get this output port, and based on that, you get virtual channel allocation, ... That way, you can reduce the router pipeline a lot. Okay. So there's another deadlock, which we haven't covered, but I'll cover very briefly, and that's called the protocol level deadlock. That's a higher level deadlock. What we've covered was a very lower level. You actually have a deadlock on the buffers. But protocol level deadlock is, you have request and reply packets, address and data packets, let's say. Because of these different packet classes, you may actually run into deadlock. Even though you may be requesting a lot, the replies may not be making their way back. As a result, at the protocol level, you may be deadlocking the system because at some point you run out of resources. Right? So by dedicating some virtual channels to these different types of packets, you could actually avoid this deadlock very easily because you always have a path. You don't intermix these different packet classes that both need to be satisfied to ensure that you don't have this protocol level deadlock. Right? That's the idea. I mean, this may be obvious, but actually existing routers dedicate different traffic classes to different virtual channels such that they don't deadlock. Okay, prioritization for different classes. Some virtual channels can have higher priority than others, and you could actually do the virtual channel allocation based on application level information, which we're not going to talk about, but this enables priority as well. Okay, let's review. This is store and forward. It looks bad. So cut-through wormhole actually reduces latency, as you can see, and virtual channel gets rid of the head-of-line blocking. I like this picture, but I think that's enough. Okay, let's talk a little bit more about buffers. So if you have buffers, actually you have other problems. You need to communicate the availability of buffers, right? How do you actually, the upstream router, when it makes a decision, it needs to make the decision, should I send this packet or flit to the next router? So how does it know there's buffer space in the downstream routers? There are many methods that are developed to communicate that buffer availability to an upstream router. It could be credit-based, it could be on-off, it could be ACK-NACK. They all have its upsides and their upsides and downsides. In this case, upstream knows how many buffers are downstream. Downstream passes back credits to upstream, saying, whenever it deallocates a buffer, it says, oh, okay, I've deallocated a buffer, so you have this much credit. But there's a lot of signaling for this to happen, especially if you have small flits. There's on and off flow control. Downstream has on and off signal to the upstream saying, don't stop sending it to me at this point. And ACK-NACK upstream optimistically sends downstream, and buffer cannot be deallocated from the upstream router until it receives an ACK or NACK. This inefficiently utilized buffer space, clearly. Actually, there's a lot of inefficiency in all of these in the end to be able to utilize buffer space. So let me show you pictorially. In this case, you send a credit back to the upstream router once you actually deallocate a buffer. There's some time that's needed to process that, and then you make that credit available. You can send the flit. And once you send a flit, you send the credit back to your upstream router. And there may be multiple upstream routers, as you can know. But this is easy because you actually partition the router based on the input channels, right? If your router is not partitioned based on input channels, you cannot do this easily, actually, because you need to send credits to multiple places, and you need to be much more conservative than you are. Okay, so it looks like this, basically. So there are clear processing delays and also credit delays. So this is called credit round-trip delay. I'm not going to go into this. But basically, it's the time between when buffer empties and when the next flit can be processed from that buffer entry. That's called the round-trip credit delay. If there are few buffers, this delay increases a lot. So you need to size your buffer such that this delay is minimal, or at least minimal for your purposes. It's also called a credit turnaround, because you're really turning around some credits. So your buffers actually are usually larger to tolerate the latencies that are happening because of this. Larger than needed, in fact. So let's look at on and off flow control. In this case, downstream has on and off signal upstream. You send a flit. There's an off threshold that's reached. You send an off signal, but it takes time for that off signal to propagate to node 1. So in the meantime, it's actually sending flits. So you need to actually size that off signal such that you can buffer these flits that are being sent during that time frame of communication. Okay, at some point, this off signal gets processed, and this doesn't send a flit at that point. and this sends some flits over here. See, there's no flits that are being sent over here because it's off now. It knows that there's no buffer space available. And another threshold is reached, and it sends an on signal. Now you can send me flits again because I have some buffer space. And as you can see, this doesn't happen for every flit. This happens for a number of flits to tolerate that delay of signaling. Okay, so clearly there is delay. And you can actually look at this in more detail. Okay, so let me cover performance also. I think we can leave 2 minutes for whatever you're going to do next week. But I think performance is important. Any questions, by the way? It's all clear. Hopefully these are relatively simple concepts, right? But to show you, there is actually a lot of overheads in this network. And this is a simple one, actually. There could be much more complicated ones if you want to optimize for performance. Actually, performance we've covered before. If you think about, I don't remember in which lecture, but in one lecture I drew this curve. Basically, this is actually a performance curve that you see in many networks. You have an injection rate into the network, or load on the network. Flits per second per node could be one. Or the fraction of links that you utilize, offered load, things like that. This could be, but injection rate is usually flits per second per node, packets per second per node, how fast you're injecting. And this is your latency. And the curve looks like this, always. Always a strong word, but always. But basically, there's some zero load latency. This is your zero load latency. And of course, what is latency? This is average packet latency, assuming some sort of traffic. So you need to assume some sort of traffic over here. Usually, well, it could be uniform random traffic. If you read the paper that I assigned to you, it actually has many different traffic patterns. But uniform random traffic is interesting. It doesn't assume any communication pattern. It's random, basically. Any node can send to any node in a random manner, and that distribution is uniform across all the nodes. But this could be, you could also have a curve for nearest neighbor communication patterns, in which case this curve looks like this, usually, if you design a good network. It could be a hotspot. You could have one node, all of the nodes in the network sending at a very high injection rate to a single node, in which case the curve looks like this. Meaning you actually, your latency shoots up very quickly because you're not really utilizing your network path really well, right? Basically, regardless of your traffic pattern, the shape of the curve looks like this, but where do you end up in terms of the exact x-axis and the y-axis differs. So where do you start in this x-axis? So, this is going. So there's some minimum latency that's given by your topology. That's your topology tax. There's some minimum latency on top of that given by your routing algorithm. You get a tax on your routing. And then you get taxed on the flow control also. So your minimum latency is really determined by all of this. Your topology, routing algorithm, and flow control. And there's some minimum latency that you cannot go below because all of those added some taxes to you. Okay. On the other hand, your throughput, maximum throughput, is dictated by your topology. And you get some taxes on that because of your routing inefficiencies, because you may not always have good choices. And you get some taxes on that because of your buffering and flow control choices. And your saturation throughput, this is also called saturation throughput at this point, it's asymptotic over here, is really dictated by all of those again. And all of your design choices matter for this curve in the end. And ideally, you would like to operate not here, clearly, because there your latencies are very high. You really want to operate somewhere here. And the key question is, how do you actually operate somewhere here? If you're operating here, you're oversubscribing your network. And internet, actually, this is called congestion collapse, if you've ever heard the term. It basically says you're operating somewhere here. You collapse the network. Even though you may be injecting stuff, you're not getting responses back because you're really operating very close to your saturation throughput. And as a result, your latencies are very high. Okay, so that's very fundamental. So ideal latency looks like this. Basically, it's solely due to the wire delay between source and destination, as you can see. So you have Manhattan distance between source and destination, which is the distance between 2 points measured along axes at the right angles. That's really the XY distance. And there's some propagation speed. So that's your delay plus your packet size divided by the channel bandwidth. Right? You could actually do these calculations yourself. It's very simple. A bit boring also. But this is ideal latency, right? This doesn't take into account overheads because of the router. Because this is kind of dedicated wiring, if you think about it. You don't do any routing over here. because you're only dependent on the channel bandwidth. If your channel bandwidth is the same as your packet size, it's only one packet that you're sending. And yeah, okay. But the router adds some more tax over here. This is the number of hops that you need to go through, and this is the delay through the router. Plus, there's some delay through contention, which is actually a much more complicated equation than this, because that really depends on the contention patterns that you have in the network and the router. So the actual latency actually can grow quite higher. So ideally, you would like your latency to be this way, but usually you get this curve in the end, right? Okay. So clearly, this is one example, network performance. It's actually a nice way of reasoning about the network only, but and we've discussed these metrics, basically, packet latency, round-trip latency, saturation throughput, but none of these consider application-level performance, system performance. This is also affected by many other things that we've discussed in this course, like interference among threads in applications, right? It's not just about latency or throughput. It's really about system performance, execution time in the end. And I think we'll talk more about this in the early part of next week. So in the early part of next week, what we will definitely do is finish up routing and interconnection networks. We'll focus a little bit more on chip networks, because it's really important to think about how things scale on chip. If you think about the next architecture that Subbus discussed yesterday, actually interconnects are actually critical for that architecture to scale. Because if you keep adding stacks on top of each other, in the end, you're limited by your interconnects, right? You may be connecting those stacks together at the very fine grain, but how do you connect them all the way in the end? So actually, the interconnect is going to become even more important, in my opinion, as we solve the memory problem more and more. That's, again, it's Amdahl's law, right? We solve the computation problem today, maybe. The memory is a big bottleneck. We solve the memory problem. Now, interconnect will become a big culprit. In fact, interconnect is already becoming a big culprit in the big data center space. Memory is a big culprit over there. But storage has been a huge culprit in the data center space. Once SSDs replaced the hard disk drives, interconnect became a much bigger bottleneck over there. Memory is still a bottleneck. That's not solved. But interconnect became a much bigger bottleneck than storage. Now, if emerging memory technologies like what we've discussed replace the SSDs and storage, persistent storage, becomes much faster than existing SSDs. Now, interconnect will become a much, much bigger bottleneck in the data center and high-performance computing space. So it's good to put things in perspective. It's a bottleneck on chip, but it's also a much bigger bottleneck in the data center supercomputer space as well. Okay, so what do we do next week? I have 1 more minute. That's great. You can leave your questions for next week. We're going to finish this next week. But apart from finishing this, I think we'll spend the lecture on Wednesday. Do you want to have a new topic, or do you want to just ask questions in general? Any thoughts? What's the new topic? Well, I have a lot of choice. What would you like? We may start it, but we may not be able to finish it. Or an alternative is actually you asking questions on anything related to architecture, including the topics that we've discussed. But it could be also other things. It could be more free form. What do you prefer? I mean, clearly we're going to finish this lecture. And it will take time. No choice? Okay. There's one opinion. Any other opinions? So we can have a discussion session, I think, on Wednesday after we finish the lecture. Unless somebody speaks up and says they want to hear about multi-threading. I've given you one topic. There you go. I see. Oh, you have to counter him. So yeah, we're 1-to-1. So who wants to have a discussion session where they could ask any question? So Thursday, I think we'll do a review session for sure for the exam. So I don't want to cover a lot of new topics, frankly. If you ask me, I will choose the first one because I think this is a very clean way of. We've covered everything I really wanted to cover, Of course, there are a million things that I can cover also. Like we could actually have a lecture on dependable system design, which is interesting, but it'll take some time. Or you could actually ask questions on anything that we've discussed. We could talk about real system designs. What does an architect do? Jobs, internships in architecture, research in architecture. I could actually talk about some research directions in the field. Based on everything we've discussed and some things we may not have discussed. That could be interesting.
Or maybe the research opportunity and the job opportunity.
Okay, I mean, we could do that, sure.
Yeah.
We could structure it as a more discussion session, and I can have some starting thoughts. Does that sound good? It seems like more people are agreeing with this. I can see a lot of heads nodding. Okay, so let's do that next week for Wednesday. And Thursday, we may actually continue the discussion depending on how things go and have a review session or whatever. Yes?
Can I also offer something else?
Sure.
Is there anything in discussion about underlying mathematical foundations?
That sounds like a great question for next Wednesday. There you go. So this is the kind of discussion we can have next Wednesday. It seems like people have questions. Okay. Have a good weekend.